this computer. I should have done it. I should have done it yesterday, but I didn't. I didn't really think about it. You know, I'm kind of free form when I go on these things. So
I started recording certain sections of it just with my phone on the screen.
okay.
But I thought, well, that would be nice just to have it on video.
All right. All right. So how does the feed point impedance change? It goes up. All right. As an antenna gets a horizontally polarized antenna versus a vertically polarized antenna, the polarization is the direction of the cable with respect to the ground. If it's horizontally polarized, it's parallel to the ground. If it's vertical, it's perpendicular to the ground. If you have a horizontally polarized antenna, you have lower ground reflection loss. It's just a function of the antenna. The pattern of an antenna is very important. Now, so notice we have a half-wave dipole. On the left, we basically make a figure-8 pattern at right angles to the antenna. And in fact, it's a figure-8 pattern, but it's actually a donut known as a torus. So if you were to look at the actual pattern, it's strongest perpendicular to the wire. And as you go away from the center axis, it weakens. And along the axis of the wire itself, you have virtually nothing being emitted.
Okay, wait a minute, Scott.
Yep.
You said horizontal antenna has a lower ground reflection loss. What's that mean?
Well, if you think about it, you take a look at this horizontal antenna, a lot of the energy is aimed toward the sky, right?
I don't know.
Well, what's the radiation pattern coming off an antenna? Look at that drawing.
Are you talking about a wire antenna spread out?
Well, no, I mean, if you have if you just have an antenna that's either like this or like this, this antenna that's on the screen on the left, right here, this is just a half wavelength piece of wire. The antenna pattern is going to be perpendicular in the shape of a figure-8. So a vertical antenna is going to have, if we look at it from the top, its radiation pattern is going to be the same in all directions because of symmetry, which means that part of it is going to be going up and part of it is going to be going down. Well, and it's going to be going down all around the antenna in the same orientation. So unless you have a perfect ground, if you want to think of it this way, your radiation pattern is scraping along the ground, at least the bottom half of it. Does that make sense?
Yeah, you're talking vertical, not horizontal, right?
Well, I'm talking both. Now let's take an antenna that's horizontally polarized. So I'm going to erase this. So we're going to take a horizontally polarized antenna like this. So if we were to draw this in 3 dimensions, some of our pattern would be going this way, some would be going this way, some would be going up, some would be going down. Some would be going this way, and some would be going this way. And realistically speaking, there is no energy going in the axis of the antenna itself, because that's not what dipoles do. Dipoles make energy perpendicular to the wire. So it goes this way, and this way, and this way, and this way. So how much of the energy actually scrapes along the ground? This and this, right? Well, it's not nearly as much as with a vertical, and that's why. So your ground losses on a vertical are higher, unless you've got a really good ground plane. Like you've got like 100 wires buried in the ground, or you've got a big piece of metal like the roof of a car. If you've got a good ground, a vertical works great. Like if you've got seawater works wonderfully. Okay, how does the antenna height affect the horizontal? We'll call it azimuthal radiation pattern of a horizontal dipole. So as you go down toward the ground, a dipole becomes less and less directional. It becomes more and more omnidirectional. So, and that's largely because of the fact that it's now interacting with the ground. So it becomes even closer when, and what does omnidirectional mean?
Oh,
All directions. Yeah. So it basically radiates. It's kind of like a blob in all directions.
Scott,
Yes.
I'm sorry. Could you just repeat that point you just made, that when the antenna becomes more omnidirectional, when does that start occurring?
Below a half wave. And the
Below
lower
a
you,
half.
yeah. And the lower you go, the more omnidirectional it gets. And on top of that, as you go down, as it lowers, the feed point goes down.
Oh, okay. I'm sorry. As you look,
feed-
as one goes below quarter wave.
As the antenna goes lower and lower toward the ground, the feed point impedance continually drops.
Oh, as you
so-
physically lower the antenna.
Yeah. So this antenna in free space has a feed point impedance of 72 ohms. As it goes toward the ground, the antenna impedance drops.
Hmm. Okay.
In fact, a shortened vertical has an impedance of 36 ohms. It's half of that over a ground plane. And as you get shorter and shorter, your vertical impedance could drop. And for instance, if you have an electrically short vertical, the impedance could be like 3 ohms. This is a particularly interesting issue when you have a short antenna and you have a car, because this might have an impedance of 3 ohms and your ground impedance might be 2 ohms. Well, you start looking at those numbers and the impedance to ground is almost equal to the impedance of the antenna itself, which means a good amount of your power is just being wasted. It's going into the ground as opposed to up the antenna.
so Scott, you
Yep.
know I've got a 6B TV vertical on a metal roof.
That's
How
great.
would I measure the impedance of that at the feed point?
You get an antenna analyzer and you go up to the antenna and remove the cable and hook up a short cable and use the antenna analyzer.
Does that shows you the impedance or the VSWR? I don't
It
remember
shows you the
which.
impedance. If you've got a good antenna analyzer, that'll actually show you the complex impedance.
Oh, interesting. Okay.
Mhm. Okay, what's the approximate length of a
I got a
quarter
question.
wave?
So with the impedance, does that have anything to do with which frequency you're transmitting on? Or are they all the same impedance?
I mean, if you're saying is a dipole a dipole? If it's a
I was
half wave,
thinking-
if it's a
I was
half
thinking-
wave,
yeah.
a half wave dipole is a half wave dipole. If you pick a different frequency, you end up with a different dipole.
Okay,
And
so when
and
you're using your antenna analyzer, it's going to give you the ohms at that frequency,
Correct.
like at the optimal frequency. So then if you're outside the like,
If you're away from the resonance of the antenna, you'll have something different.
okay, gotcha. So it's still going to be that. So that 72 ohms is the minimum ohms. at
Not
the resonant
necessarily.
frequency.
The 72 ohms is what it is. That's what theory predicts at the resonant frequency.
Okay,
And depending on what frequency you are, it could be lower, it could be higher.
hmm.
And it could be complex. It could be R plus JX at a given frequency. And you can predict it. You can do modeling. You can also just measure it and see what it is.
Yeah, all right.
Okay, so now we're going to do verticals. A vertical, notice a vertical is 234 divided by the frequency. That's because it's a quarter wave, not a half wave. Notice it's a half of that. So if we were to go on 10 meters, we go 234 divided by 29 or 28.5 megahertz, we get about 8.5 feet. And what's nice about that, now we'll just go with 8 feet. What's nice about that is that a quarter wave 10-meter vertical is really short. That you actually can put on your car, which is why so many people will operate on the 10-meter band mobile. And it's actually very close to the CB band. So the CB band lends itself well to mobile operations. If you're going to put in a radial field, you want a radial field typically to be on the ground, like on the grass, but typically your lawnmower will chew that up. So you want to bury that a couple of inches down. And ideally, your radials are a quarter wave at the lowest frequency you want to operate. So if you are on the 10-meter band and you want a radial field, your radials would be 8 feet long. If you're on the 80-meter band, your radials are a quarter wavelength long. Your radials buried in the ground will be 66 feet
meters.
long. 66 feet long.
There you go.
So you have to have a lot of room to put down radials that length. Okay, so if you have a feed point impedance right here of 36 ohms for your quarter wave vertical, you want that to go down. What you would do is you would actually take these radials and bend them downward at about a 30 to 45 degree angle. That actually increases the feed point impedance up toward about 50 ohms, which is why you'll find a lot of quarter wave 2-meter antennas that are built that way. Okay, now we're into directional antennas. What antenna would be best for minimizing interference? The reason that we would use a directional antenna is because it looks in one direction. If the fundamental section, the middle part of a Yagi, for instance, is a half-wave dipole, then we have a reflector, which is about 5% longer, and a director, which is 5%, roughly 5% shorter. And these spacing in between them is about 0.2 wavelengths nominally, plus or minus a little bit, depending on how you're building it. That has a main lobe this way, because you'll remember a dipole looks like that. What this does is it takes some of the energy that is headed backwards and redirects it forward. These are parasitic elements. They radiate along with the main element, with the driven element as it's called, and they send more energy toward the front. Once you do that, there is a main lobe this way and a small lobe this way. This is the front, this is the back. If we were to measure the strength of the front versus the strength of the back, we end up with a ratio called the front to back ratio, which is a strength of how, which is a measurement of how much energy is going forward versus going backward. The better your antenna, the more gain it has, the better the front to back ratio, which also means that you won't typically hear stuff off the back of the antenna very well. So that's a largely unidirectional antenna. So a directional antenna is really good for minimizing interference. The effectiveness of an antenna is measured in decibels. Our reference is a dipole. So this is known as dBd. So your Yagi antenna might have a gain of 10 dBd, which is 10 decibels in the forward direction, better than a dipole. There's also something called dBi, which is something known as an isotropic radiator. A dipole has a gain of 2.15 dBi. An isotropic radiator is an imaginary antenna that is truly omnidirectional in every direction. And as we know, a dipole radiates in the shape of a donut. So a dipole is actually 2.15 dB better in this direction and this direction than this imaginary reference antenna, which is known as an isotropic radiator. So gain figures, if you look at an antenna for a Yagi, the same Yagi would have a gain of, let's say, 10 dBd or 12.1 dBi. That's the same thing. The dBi measurements are going to be 2.15 decibels better than the dBd. So when you read the reference manual, you have to know that that's the case. Okay, front to back ratio again is the power radiated in the front direction versus the back direction. The main lobe of a Yagi, the front direction, that's the main lobe. How long is the main element? The driven element of a Yagi, that would be a half-wave dipole. Reflector is longer. and the directors are shorter because they radiate in a parasitic way. This one, because it's extra long, reflects the energy, and these guys push it forward. How do you increase the bandwidth of a Yagi antenna? The way to increase it is to get more current into it, which means you need to increase the surface area. So if you make your antenna elements big versus small, you increase your bandwidth. If you can put more directors on the antenna by increasing the length of the boom, you increase your gain. If you add more directors, let's say you have a 22 element Yagi, it's not a linear thing. Everyone does not give you X amount of decibels, but the more elements you add, the more gain you have. You can also vary the spacing of the elements on the antenna. And there are optimization characteristics for doing this. Again, I gave about 2/10 of a wavelength between them as optimal, but there are different calculations that say it might be 0.15, it might be 0.25. So these are numerically calculated by computer in a lot of cases. Some are done experimentally that show that certain ones are better than others.
So does this have to be tuned to the band you're at
Yes.
10 meter, 20 meter,
Yep,
40 meter?
It does, which is why if you have a multi-band Yagi, you'll have multiple different elements out there on the boom that are usually different lengths. How does the gain of two 3-element horizontally polarized Yagis operating in parallel improve things? Well, okay, this is something that we would have. Let's say we have just a dipole here and a dipole here. We have this pattern coming off this dipole and this pattern coming off this dipole. Each of them actually has a half of the energy, but this one's sending energy this way, and so is this. And by the time they get over here, we space these out a half wave so that when the energy from this one gets here, this one has traveled an extra half wave to get there. So if our wave looks like this, our second wave, when it gets there, looks like this, way out here. So if that's the case, what is the sum of those signals?
0. They cancel each
Zero.
other out.
That's right. So basically, this is called an array factor. And what it does is it gives us, because if the energy is not going up here, where must it be going? It has to be going that way. So what this actually does is this gives us a gain of about 3 dB, which is doubling the energy, broadside to the antenna. So this is true with dipoles. This could be Yagis. Basically, if you take a pair of Yagis and do this and space them a half wave apart, what you will get is a 3 dB improvement over either one. The next one is what happens if you vertically stack a pair of Yagis like this. So this is on a tower. What happens if you vertically stack the Yagis? Each one has an antenna pattern that looks like this. The effect of doing this is that up here and down here, they cancel, and your ultimate pattern looks flatter. So it narrows the main lobe. Essentially, the elevation is such that instead of shooting stuff toward the ground and shooting stuff toward the sky, you shoot more straight ahead. And that is why people will build an array, which is, for instance, a 6/6 Yagi antenna. If you look up 6/6 array, what you'll see is a 6-element antenna stacked a half wave directly above another 6-element antenna. And the way they're fed in phase cancels the energy going up and down. So a lot of really big contest stations will do this. Some actually will have 6/6/6 which multiplies it multiplies the effect even more, because they want that low angle of radiation.
So is a dual stack 3 dB more?
Yeah. And it squeezes the lobe down, which makes it even more effective, because the stuff that's aimed toward the sky can't travel as far once it hits the atmosphere. And we'll get to, you know, angle of incidence and things like that in a little bit. Okay, what's the advantage of a gamma match with a Yagi antenna? A gamma match is a matching device that allows the driven element to actually be connected to the boom mechanically, which is really nice because it doesn't have to be insulated. Insulators are typically plastic and they can break. So a gamma match, again, permits you to actually not separate the driven element from the boom.
What is meant by gamma?
Gamma is really the shape of the matching device. So I believe it looks something like this. So you basically have put the center here and you feed this at the a little bit apart. So that's known as a gamma. Now there's another match called a hairpin match. A hairpin match is a shorted transmission line stub placed at the feed point of an antenna to provide impedance matching. That's also known as a beta match. A hairpin match kind of looks like this. So you feed here and you feed here. This is and actually this antenna is now broken here. This is what we typically do when we build a tape measure Yagi. We'll feed this side and we'll feed this side, and then we'll actually have a little shorting stub. And because it's at RF, a short is not necessarily a short, is it? It doesn't directly short it out like you would think, because it actually has some length to it. Whoops. And the length actually means that you have a wave traveling on this antenna, which means that those 2 points are not at the same voltage. If this was DC, that would be a true short, but that's not how it works at RF. Because every piece of wire that you have, what can you do with it? You can draw waves on it, right? Well, if you know that this is at voltage, you know that this is at 0 volts. So this is kind of like, if you're starting to play with antennas, this is what you begin to work with, that any piece of wire at any length, you can put currents and voltages on and figure out approximately what it's going to be. This is also why it's important to have, if you're going to be doing grounding at a station, it's important to keep the wires really short, because if you don't do that, what will happen is you can end up with a wire going to ground that looks like this. Here's your equipment. Here's your wire going to ground. And let's say this is 100 feet long. What's 100 feet of wire?
Nice
Lot of
antenna.
resistance.
That's a really nice antenna. Yeah, so that's not a very good RF ground. You know, if this was 8 feet long, yeah, okay, that's a pretty good antenna. That's not a very good antenna. If it's 100 feet long, you've got a problem potentially, because you can start looking at, okay, I'm going to make waves. Well, okay, well, this is at 0 volts. What voltage is my radio at? Not only is it potentially not at 0 volts, but it changes depending on the band you're on, which means that it might be at 0 volts at some and not at 0 volts at others, which is very, very challenging. It gives you a little zap on the lips when you touch your microphone.
So are you talking about the chassis grounded?
Yep. I have received that little shock myself. Okay, so we're going to do a quad antenna. This is a quad. So this is a full wave loop driven usually down here. Each at each corner of the quad is a quarter wave long. And when you're building a 2-element quad, here's your reflector. It should be 5% bigger than the driven element. A 2-element quad is equal to a 3-element Yagi.
Okay, what do you mean by 5% bigger? How is that measured?
Every length is 5% bigger. So if you know that your antenna, your length of your antennas is a quarter wave on each side, it's 5% longer. So
Okay.
you have your mounting right here. Here's your boom connecting the two. This is 5% bigger. This is your reflect, and that's your reflector. So
5%
why do
on
you?
each side or 5% overall? That's what I was asking.
Yeah, I don't think it's so much matters. I mean, most people will make it a square because it's easier to make. Because then your spreaders can be the same size. So let
Right.
me ask this question: why is a 2-element quad equal to a 3-element Yagi? Which has more gain, a full size loop or a half wave Yagi or half wave dipole?
Full size loop, probably.
Full size loop. So because you begin with a little more gain, this is equal to this. Because you begin with more gain in the first place.
Does the second element 5% need to be a quarter wave away from the first?
Typically, yeah. I mean, there's optimization. It can be as little as 0.15. It could be as much as 0.3, depending on whose math you're following.
So are these things oriented perpendicular to the ground? So it'd be like if you're holding a hula hoop up and like pointing it around.
Yeah.
So
exactly.
What happens if you have it so like the hula hoop would be flat?
If
Like,
it's laying horizontally, then your radiation pattern goes up and down.
Okay.
Which doesn't really help you a whole lot. But sometimes it will, depending on if you have a very short antenna, like a very short loop. Then if it's electrically short, then your radiation pattern is going to be actually in the plane of the loop. And that's actually the basis of something called a mag loop. So if you see that, that doesn't follow the same rules. But that's a very electrically small antenna. All right, so we are on to specialized antennas. We are doing something called an inverted V. An inverted V is a half-wave dipole that looks like that. And the reason you would want to do something like that is, let's say you have a tower or a really big tree, you only need one support point. And then let's see, a horizontal loop antenna. What is the combined vertical and horizontal polarization pattern of a multi-wavelength horizontal loop antenna? Okay, so we're going to make a horizontal loop antenna. And this is multiple wavelengths long. So this is not a small thing. This is like, 300 feet if you have enough space to do it. And what you're going to end up with is an antenna that is omnidirectional and has a fairly low radiation angle. So this is a very big antenna, but it has a low radiation angle. So a big horizontal loop is a very good DXing antenna because it has a low radiation angle and it's almost omnidirectional. Okay, a log periodic antenna. So here's our Yagi. Here's our, let's say our 6-element Yagi. How many frequencies is this designed for? One frequency. Okay, now if I were instead to take all these elements and make them logarithmically related so that I have a really big one in the back and then they get a little bit smaller every time. This is our classic television antenna. If you think back to old TV antennas, because those are designed to operate at a very wide array of frequencies, almost makes like a triangle. So at any given set of frequencies, because they're logarithmically related, only a couple of elements are involved, which means that the gain is not particularly high, but it's very, very wide banded. Again, moderate gain with a very wide bandwidth. So what describes the log periodic antenna? Element length and spacing vary logarithmically along the boom. The end result is to make something that looks like a shape of a triangle.
Do the elements that are not
They're-
involved with transmitting interfere, like to
They-
lower the gain of
they
the
don't.
other?
They don't, they're just not involved. But the tricky thing with this antenna is that every element is driven. There's nothing that's parasitic. Every element actually is connected to the power. And the ones that don't get involved just sort of don't exist
Because they don't resonate, and so they're
because they
not.
don't resonate. They're not even close to resonating.
So can you get an old TV antenna, just string it up on a HF
Sure.
radio and make?
You have to, well, not an HF radio, a VHF radio, because old school TV was VHF, UHF. Now,
Okay.
what you'd have to be concerned with is that it can handle the amount of power that you're transmitting. That's the big concern. And I would put it on an antenna analyzer to make sure that it worked.
Oh, I got you, because the TV antennas are only designed to receive. They're not
That's
really
right.
designed to
They're
transmit.
not designed to handle power.
Gotcha.
Okay,
And
NVIS.
the design for a different coax cable too. I'm willing to bet
And they're usually designed for like 300 ohm cable.
something. Yeah.
Yeah. All right. So NVIS. NVIS is often used by the military. It means near vertical incidence skywave. The closer you get to the ground, the more of your signal goes straight up into the air. If you're trying to contact a helicopter that's flying overhead, this is a great thing. So if you take an antenna and put it between 1/10 and 1/4 of a wavelength above the ground, most of the energy will go up into the air. Now, this can actually be useful for 40 meters during the day or 80 meters when most of your communications are going to be fairly short anyway. So if you want to do 40 meters during the day, you can do NVIS, and the skip zone, because of the angle that the energy goes up, might be only a couple hundred miles. So that's for short skip near in communications, because an NVIS puts out energy at a very high angle. A beverage antenna. Okay. A beverage antenna is also known as a traveling wave antenna. And this might be, let's say, 6 wavelengths long if you have a lot of space. This is useful for the low high frequency bands. So let's say 80 meters and 160 meters. If you have a lot of room, here's your feed point, and it's a single piece of wire, and it uses the ground for the other leg. Essentially, because it is so long and the waves look like this actually causes it to function as a very directional antenna. It receives really well in the direction that it's pointing, but it has to be like many wavelengths long, and that's known as a beverage antenna. These are never used for transmitting because they're so close to the ground typically that a lot of the energy will just disappear into the ground. But for receiving, you can deal with that, with the sum of that loss, and instead you get a lot of gain in one direction. So a big station, a station that's really serious about, let's say 160 meters, might have a quarter wave full size radio, a quarter wave full size vertical, which is 130 feet tall, and then beverages going out in many directions. And they have the ability to switch between antennas to get directional receiving.
I did some quick math, and 6 times the wavelength of 160 meters
Pretty
is almost a
freaking big.
kilometer.
That's
That's
right.
almost a kilometer.
That's right. If you have a lot of land, it's a great thing to do. A lot of people buy big pieces of property so they can do that. Let's say Oklahoma, Kansas, you know? What's a disadvantage of a multi-band antenna? Well, a multi-band antenna is not going to be tuned. It's not going to be resonant on any frequency. If it's not resonant on any frequency, then it receives all the frequencies pretty well. So it has poor harmonic rejection. And a harmonic is, let's say you're operating at 10 megahertz. That means that you'll also operate at 30, 40, 50, 60, etc. All the multiples of that fundamental frequency. A multi-band antenna might actually put out some energy at these other frequencies because it's not a tuned device. So poor harmonic rejection. The purpose of an antenna trap. So what do we know about this antenna right here? Why would we do that? That's called loading. What's the purpose of loading? Everybody,
Changes the electrical length, or the,
right? Changes the electrical length, but not the physical length. Okay. Now we can also do this. Hold on. Let's do this a different way. Okay, so here's our feed point. What would be the point of doing that? What does that little circuit here look like?
looks like inductor
what-
and a
That is
capacitor.
called an LC circuit. And what can we do by picking those elements?
Filter.
We can make a filter, yes.
Or
Okay, so
does
at a
it impedance
particular
match also?
frequency. What?
Say-
Not really, not in this
Okay.
case. I mean, it can be, but really this just functions as a filter. What this does is, let's say we're operating at 3.5 megahertz. And this antenna, its full length, including the filter, is appropriate for 1.8 megahertz. What this does is, if this LC filter is tuned so that it has a null at 3.5 to 4 megahertz, what will happen is this is the end of the line for that frequency, which means that this properly cut piece of wire is now a quarter wave at 3.5 megahertz. The trap, as it's called, allows energy to pass and get to this other section. And that other section, included with this first section, is appropriate as a quarter wave for 1.8 megahertz. So by adding a tuned filter, you can create sections of your antenna that will operate at different frequencies. And that's known as a trapped antenna. Those are antenna traps.
Pretty cool.
And we can have a multi-band Yagi that, if you look at a multi-band Yagi, it might look like this. Each part of the driven element looks like that. Each part of the reflector and directors might look like this, and this is a trap, and this is a trap. And this section is your 10-meter section, this is your 15-meter section, this is your 20-meter section. So each one of these, this is your 10-meter trap, this is your 15-meter trap. So the energy for 20 meters goes through the whole thing. The energy for 15 meters passes through the 10 and gets stopped by the 15-meter trap. And that's known as a that would be something similar to a 3-element tri-band Yagi. And the way that you would get a tri-band Yagi is by adding traps to it. Now, they're also exposed to the weather. They get filled with bugs. Bugs think that they're really cool. And they add extra weight, but if your mechanical antenna is designed for it, then you're good. What's the feed point of an end-fed half-wave antenna? We kind of covered this yesterday. Covered this today, actually, too. As you get toward the end, here's your current, here's your voltage. You feed it way at the end, and your Z is about 5,000 ohms. Which is why, or let's say 2,500 ohms or whatever it happens to be, which is why you need an impedance transformer to feed power into that. Okay, an electrically small loop. We sort of mentioned this a little. An electrically small loop. Whoop. This would be like anything smaller than 1/3 of a wavelength in circumference. Its radiation pattern is in the plane of the loop. So you have a null above and below. So basically, if you want this would be a horizontally polarized antenna because it's parallel to the ground. If I made it vertical, it would be up and down and nulls this way. This is actually a really useful antenna for doing direction finding if it's a really small antenna, because you know if you turn your antenna at a certain way, you will get nothing in the nothing going through the loop. So you know you have a null there. So it's not looking for where it's strong, it's looking for where it's weak. A screwdriver antenna. Okay, this is a special kind of mobile antenna, which actually looks like this. There's actually a screwdriver motor in the base of the antenna. What this does is it has a little shorting plate and it jacks the whole thing up and makes a contact with a coil. As it moves up, the coil changes position with respect to the shorting, which means you have more or less coil exposed.
So
by
it's like
doing
a
that,
rheostat. Is that what they used to call it?
yeah, kind of, yeah.
Okay.
And by doing that, what you basically do is vary the base loading inductance because a coil is an inductor, and that changes the resonant frequency of the antenna. So, but it basically varies the base loading inductance by use of a 12-volt screwdriver motor. All right, finally, in which direction is the maximum radiation from a portable UHF VHF halo antenna? All right, a halo antenna is an electrically small antenna. And what do we know about an electrically small antenna? A loop. What direction is it going to work?
Omnidirectional in a plane.
In the plane of the antenna. And what's cool about it is that it's actually horizontally polarized. It's not vertically polarized, which is actually very useful for long-range omnidirectional communications. So weak signal works really well with a halo. Okay, next, radio wave propagation. What is the significance of sunspot numbers with regard to HF propagation? And we're on page 40. We're on page 50, by the way.
More sunspots means a better chance of HF propagation. Yes.
Right. Sunspot number, A index, and K index. All right. So sunspot number, and then there's also 2800 megahertz solar flux. Those are our four things that are really interesting.
Excuse me.
Okay, so our sunspot number, that is the number of sunspots that are on the face of the sun facing us. The SFI, or solar flux index, is measured at 10.7 centimeters. This is a fairly good representation of how much ionizing radiation that ionizes the RF, that ionizes the upper levels of the atmosphere that we are interested in are coming out of the sun. So this can go all the way from as low as 65, which we saw over the last couple of years, up to, let's say, 250 and higher. When those numbers start to go up, we get more ionization in the atmosphere. When we get more ionization, we get better high frequency communications at higher frequencies. This is largely proportional to the sunspot, to the sunspot number. So the sunspot number could be 0, it could be 240. That's just basically a count of how many sunspots are on the face of the sun. As we have the Earth here, the Earth is surrounded by the ionosphere. So we have our D, our E, our F1 and F2 layers. This starts at about 50 miles up. This goes to about 100 miles. This is about 300 miles. This is about 600 miles, roughly. So the D layer, which is the bottom layer, this is responsible for daytime absorption of lower frequencies. This is why we can't hear AM radio stations over long distances during the day. The E layer, which is right here, that's responsible for some absorption, and also for VHF, very high frequency communications as clouds of ions form up here in this layer. All right, so when I say ions, what is physically happening is we have atoms floating around in the atmosphere. That's what it's made of. Largely oxygen and nitrogen, molecular form. Energy comes out of the sun, hits the atmosphere. Once in a while, one of these photons of energy will cause one of these atoms to get hit. And what flies out of it is an electron. And let's say this is nitrogen. We'll have a nitrogen ion. These are electrically charged. You notice the electron has a minus charge. The nitrogen now has a positive charge. This is now a conductive surface. It's now an electrically conductive thing. And that develops up in the sky. Well, electromagnetic energy coming out of your transmitter as it shoots toward the sky may or may not hit some of these things. Depending on the amount of energy that the sun has been spitting out, that determines how many ions have formed, what the concentration is, way up here in the ionosphere. That determines what frequencies are capable of being reflected or refracted back to Earth.
Hey, Scott,
Yes.
I'm not, if you go back just a second, I don't know what the A and the K are. I wasn't
Because we're
clear
not there
on
yet.
that.
Because we're not there yet.
Oh, and SFI. I wasn't
Yep.
sure what that is either.
SFI is solar flux index.
Is the E layer where the Aurora Borealis happens?
I don't know exactly. It's pretty intense. It's probably up in that area. Yeah. I mean, basically, the Aurora Borealis comes down over the poles and goes to fairly low altitudes. But that's largely caused by charged particles coming out of the sun. But you know, our atmosphere at the toward the equator, it typically blocks them, which is why it redirects them up toward the poles and down over the top and bottom. Which is why you get polar aurora and not, mid-latitude aurora. But basically what ends up happening is that the higher the solar flux index, the higher the energy that's coming out of the sun, the greater the concentration of ionization up here in the upper atmosphere. The higher the level of ionization that occurs, the higher the range of frequencies that get bounced. So the E layer is kind of its own separate thing. You might have clouds that form, and these are actually really good for VHF, like the 6-meter band and the 2-meter band. For the high frequency bands, they basically pass through, and the E layer is not responsible for much of anything. So what this means is that if we have more sunspots usually translate to solar flux index. Solar flux index translates to more energy. More energy translates to more ionization, which translates to more good propagation at higher frequencies. So if you look at your frequency charts, you'll see that we have kind of a dichotomy of bands. There's 160 meters, 80, 40, 20, 15, and 10, and I'm leaving some out. But essentially and this is all in meters, this is wavelength in meters. As your ionization levels get better, you tend to skew toward those higher bands with heavier ionization. The other cool thing is that this actually changes from day to night. So during the day, when the sunspot numbers are good, 10 meters might be wide open. At night, when there's not much in the way of sunspots, you might be way down here. And those are really good. At that same time, the highest you may get is actually on 20 meters. And like for the last 4 years, the 10-meter and 15-meter bands have basically been stone dead during the day because there's not enough ionization to make them work. Okay, at what point in the solar cycle, this follows an 11-year cycle. Does the 20-meter band usually support worldwide propagation during the day? 20 meters is that crossroads. So even when the sunspot cycle is at its bottom, 20 meters is still usually good. When it's at its peak, 20 meters is still usually good. So 20 meters is really the workhorse of all the bands. 20 meters, it can work at any point. Which are the least reliable bands for long distance communication when there's low solar activity? That would be anything above 20 meters. So actually what we have available to us, if you look at the chart, there's also in here the 12-meter band. So 10, 12, and 15 are usually dead as a rock during the bottom of the sunspot cycle. What HF propagation conditions, what causes HF propagations to vary periodically in a 28-day solar cycle? So what goes around every 28 days?
The sun.
The sun goes every 28, rolls around every 28 days, carrying its sunspots with it. And as it does that, if one side of the sun has more spots than the other, what we end up with is variation over a period of about 28 days.
How long do those sunspots tend to last? So as it
They can-
rotates around,
They
are
can
we seeing
last
the
for
same
almost no time.
sunspot?
Yeah, they can last for almost no time. They can last for months. One phenomenon that can have a drastic effect on propagation is a sudden ionospheric disturbance. This is in the form of X-rays and ultraviolet. So X-rays and ultraviolet are what kind of radiation, everybody?
Ionizing.
And in particular, they're electromagnetic. They travel at what speed?
Light speed.
Light speed. So how long does it take for light to get from the sun to the earth? Roughly?
8 minutes.
8 minutes. So that X-ray burst, the ultraviolet burst, the sudden that flies out of the sun, takes 8 minutes to get here. So unfortunately, that means that we don't really know that it's coming because our instruments on satellites travel around the sun, and they also send information over electromagnetic waves, which means that they're saying, "Hey, there's something coming," and it gets here at the exact same time as the thing gets here because they're traveling at the same speed. So we don't know that it's coming. A sudden ionospheric disturbance affects lower frequencies more than higher frequencies. A coronal hole or coronal mass ejection is a basically a shot out of the sun, but it's not ionizing radiation. It's charged particles, and they're traveling at usually hundreds of kilometers per second, which is way slower than electromagnetics, which basically means we might have an X-ray burst coming out, and the satellite also picked up a CME or coronal mass ejection flying out of the sun. And when it did that, it says, okay, hey, it's coming. It gets here at the speed of, the information gets here at the speed of light. And basically we have 20 to 40 hours to prepare. And that might mean, okay, we know that between 1 and 2 days from now, depending on how fast it was all spit out, we're going to have all those charged particles hitting the earth, and our radiation is our ionosphere is going to be hit really hard, and we're going to have an aurora. We're going to have a high frequency radio blackout, and that does happen. And the nice thing about it is, to a certain degree, we can actually prepare. You can say, okay, here it comes. Like people said over the last 2 days, there was an aurora that was going to happen last night. The reason they knew that was because it was coming right for us. We expected high frequency propagation to get worse. I don't know that it actually did by much, but I do know that, it probably did. A geomagnetic storm. Okay, so now we're into the A and K indices. So the K index is a short-term measurement of the stability of the Earth's magnetic field. The A index, and actually this is measured over a period of 3 hours. The A index is a long-term measurement of the stability of the Earth's magnetic field. And this is measured roughly as 3 days. So this basically says the A index, the K index is between 0 and 9. The K index is a 3. That basically says that right now and over the last 3 hours, there's been some shaking in the Earth's magnetic field. It's been hit by something, and all that movement is generating some radio noise. Conditions might be a little bit not so good. The A index is a very large number, but basically you can look at this thing called the A index, and that really just tells you what it's been like for the last 3 days. It doesn't really predict the future at all. It's just kind of a smooth number. So really the K index is what's important. And let's see. What can happen if a geomagnetic storm hits the Earth? Basically, those charged particles, like from that cause the aurora, hit the Earth's atmosphere. They'll degrade high latitude HF propagation. Now, there is one good thing about that. When we have this thing called an aurora, if you've ever seen an aurora, it's really cool. Well, what happens is that the Earth looks like this, and here's the magnetic field. Notice the magnetic field kind of has a channel in the top. These particles float down here, and what happens is the high energy particles will strike atoms in the Earth's ionosphere and cause them to turn all different colors. That's the aurora. Well, the aurora is an electric thing. So let's say that we live down here and we have an antenna that points this way. We can actually take a signal and shoot it into the aurora, and it bounces back. So, and this is true on VHF. So 6 meters and 2 meters, you can actually do auroral propagation by sending it into the clouds of the aurora and having it bounce back. So when we have that high geomagnetic activity, we can actually use the aurora to our benefit. It sounds kind of interesting.
Do people like plan for that and try to do that? I'm sorry,
They do. They absolutely do. Yeah, go ahead.
Yeah, Scott, just a little bit of clarification. You're saying though that when we do get some of these coronal mass ejections and so forth, that there's other problems or interference.
Oh yeah, it's terrible. For the most part, it's awful. I've been on the air when the band totally disappeared for a period of 4 hours.
Okay.
Just went away completely.
But I thought earlier, though, it seemed though that we were also though saying that the greater sunspot activity improves the, increases the ionization in the ionosphere.
Right. Because they're two different things. It's a double-edged sword.
Okay.
The ionization is what's normally spit out, and the coronal mass ejection is all those pieces. Normally, there's lots of pieces coming out, but basically a CME is like a lot at once. In other words, just too much, and it's overwhelming.
Okay, so the normal stuff though is benefit. It sounded like it was beneficial.
Right.
Okay.
Okay, so now we have two things. We have Muff and Luff, MUF and LUF, maximum usable frequency and lowest usable frequency. So the maximum usable frequency is a function of the highest frequency that the atmosphere can refract back to Earth so you can have communications. And this is usually between 2 points. So that's known as the maximum usable frequency. The lowest usable frequency, or Luff, is the lowest frequency at which that path can still work. So what affects the maximum usable frequency? The path distance and location, the time and day and season, and the solar radiation and what's happening to the ionosphere. So what happens to radio waves with frequencies below the Muff and above the Luff? Well, if they're below the Muff and above the Luff, then you're good. So let's say your Muff is 21 megahertz and the Luff is 7 megahertz. Well, that tells me that anywhere between 7 to 21 megahertz, you stand a chance of something actually working. That's good. You have a good range of frequencies to do that. Okay, but what happens to frequencies below the Luff? So 3.5 megahertz, what would happen is that those frequencies, which I'll put in green, would get up here to the atmosphere and get absorbed. So frequencies below the Luff get absorbed by the atmosphere. And it is entirely possible that you might have a situation where you have this. So here's the situation where the Muff is let's say 10 megahertz, and the lowest usable frequency is 11 megahertz. Okay, what do you think gets through when the LUF is higher than the MUF?
Absolutely nothing.
Absolutely nothing. This is what you would call a path that doesn't exist. So let's say like you're trying to talk to somebody on the other side of the world and it's daytime for you. You would normally, because of the Muff, have to do it at, let's say, 7 megahertz. But it's the middle of the day, which means that the atmosphere is absorbing everything below 11, which basically means you can't talk to that part of the world.
So
This won't happen.
So it seems bizarre to me that the lowest can end up getting above that. Is it because one is measured with the kind of a theoretical thing and the other is the one that moves? So
they are both completely real.
And are they both moving? Or is it
Yes.
one's moving and the other one's staying?
The other one's they're always changing.
Okay.
So a lot of it comes down to what if you were to look at the day-night curve on the Earth, right? A map. And so here's day and here's night. So this part of the Earth, it's daytime, and this part of the Earth, the other part of the Earth, it's nighttime, and you have the polar regions which are lit up. So let's say that if you're trying to go over the South Pole, it's all daytime. So your maximum usable frequency might be pretty good, but unfortunately, at this point over here, it's still, at this point over here, it might be so that the lowest usable frequency, because they've been in daylight, is actually higher than that yellow line would permit. In other words, the signal would make it to right here and then get absorbed. So, because you're looking at an entire path, you're not just looking at the whole atmosphere.
Oh, interesting.
Yeah. Because it has to go through many different areas in order to make a really long distance communication. Okay, let's see. Which of the following applies when selecting a frequency for lowest attenuation when transmitting on HF? Typically, what you aim for is you go right before the MUF, right below the MUF. So that if the MUF is 22 megahertz, and you look at your frequency bands, we've got frequency bands at 3.5, 7, 10, 14, 18, and 21 megahertz. That's the one that would give you the best chance at long communications that work really well. You want to go up to and as close to the MUF as possible. What's a reliable way to determine if the MUF is high enough to support skip propagation between your station and a distant location between 14 and 30 megahertz? We have something called propagation beacons out there, which are all over the world, and they are transmitting all the time at all these different frequencies from all over the world. So let's say that I am right here, and I can hear this signal coming in on 21 megahertz. And this way I can hear 28 megahertz. This way I can hear nothing. So basically I have this one that I'm picking up, and I can hear them on 28 megahertz. That tells me that the maximum usable frequency will support communications on 28 megahertz. I would not expect to hear 28 megahertz on this particular path because the MUF does not permit it. What's a characteristic of skywave signals arriving at your location by both short and long path? Okay, short and long path. Literally, there are two ways around the Earth connecting any 2 points. There's the short way around and a long way around. And if you need to prove this to yourself, you can go grab a basketball or a soccer ball or a football or use whatever kind of ball you want and say that, okay, there's that line. This is called the Great Circle that goes around the backside. There are two ways to connect there. This is the short path and this is the long path. Sometimes you'll actually have conditions where both of them exist and you'll hear both. Well, the long path is longer, so it takes more time for the signal to get there, and you can actually hear a slight echo. You'll actually pick up both. Okay, ionospheric layers, critical angle and frequency, HF scatter, NVIS, etc. Okay. Where on Earth do ionospheric layers reach their maximum height? Well, considering that it's driven by the sun, where do you think they'd peak? If the sun is up here.
Like at noon, like right above.
Yep, where the sun is overhead. That causes the greatest amount of ionization to occur. Directly overhead, the ionospheric layers get to their maximum altitude. Okay, the F2 region. So we're going to draw again D, E, F1, F2. The F2 region is the one that is typically responsible for our longest communications because it is the highest level. If we think of these things as mirrors, which they're not exactly, but if we think of them as mirrors, that mirror will give us a longer path than that one or this one. So our maximum skip distance will be generated by the F2 layer. This is just basically geometry at this point. The approximate maximum distance that's normally covered by a hop using the F layer, single hop can be as long as 2,500 miles. And again, that's just due to geometry. The E region, which is right here, that's about 1,200 miles. So again, geometry. The ionospheric layer that's closest to the surface of the Earth would be which one?
D.
The D. And what is the D layer good for?
Can't remember.
Not much.
No.
It absorbs everything below 10 megahertz during the day, which is why we cannot hear AM radio from long distances during the day. And as soon as the sun goes down, you can pick up Salt Lake City and San Diego and Los Angeles and Calgary. So the D layer, in addition to that, the bands that work, our bands that are below 10 megahertz are 40, 80, 160, 60 meters. Those are below 10 megahertz. These are basically dead during the day because of the D layer. Makes it very difficult to communicate. What is the term? Go ahead.
Scott, so you talk about F layer of 2,500. Is it F1 or F2 or
F2.
what?
F2. The F1 layer is kind of like a subset. And at night, these actually merge into just a single layer. So there may be some reflections out of the F1 layer, but we usually think of it as the F2. What is the critical angle? Critical angle is the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. So that means if our angle of attack is like this might actually be so high that we get a little bit of refraction, but it just shoots off into space. Get a little bit lower, maybe it goes off in this direction. We still can't hear anything. So what does that mean for this zone right here? Everybody?
Incommunicado.
That's right. This would be known as a skip zone. And typically we don't hear stuff within the skip zone, which is why if you look at a map of the stations that you can hear during the day, you will pick up, for instance, using a digital mode that maps it, from here, you might pick up people in this range. And then you'll have another dead zone. And then further out, you'll see another band. Whereas you basically have this big old dead zone right here. And that's why you have the big dead zone, because the angle that would be required is too steep. That's known as the critical angle. What type of propagation allows signals to be heard anyway in the skip zone? Well,
scatter. That's going off everywhere.
scatter. That's right. And in fact, what happens is that this ionosphere is not a mirror. It actually is made of individual particles, individual ions, individual electrons, and each one of them has the ability to kind of do this and bounce things backwards. So you might actually pick up a station a couple 100 miles away because of scatter. Why are they weak? And that's because most of these particles tend to reflect everything back the way that you would expect them to be. But some of them don't, which is why scattered signals are usually very weak. A characteristic of HF scatter, because it's so sporadic, it comes and goes. They sound like they're basically hovering, wavering, coming in and out, and that's because most of the energy is not getting scattered back. Any energy that's scattered into the skip zone through several different radio wave paths, again, they end up sounding very distorted. Okay, NVIS, near vertical incidence skywave. NVIS is short distance MF, which is like 160 meters, medium frequency, or long wave HF propagation, so 80 meters, 160 meters, using very high elevation angles. So basically your signal, instead of doing what you would normally do, you come down here and you go like this and you shoot signals up. And that's not the most efficient way of doing it, but some of it's still going to come back down. And this would be called NVIS, or near vertical incident skywave. So it's almost straight up and down. And the signal that comes down is going to be coming down almost vertically as well. Again, really useful for talking to a helicopter up here, or talking to a satellite up here, or if you're lucky, a little bit of the signal will actually come bounce down back to Earth. So that's very, very short distance. Okay, so we're on to amateur radio practices. So how about a 5-minute break, everyone?
Yes, please.
Okay, let's do that. All right, that was an awesome break. Do, 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 do. All right, everybody ready to go?
I guess.
All right, here we go, everyone. We're into amateur radio practices, which is page 57. Station operation and setup. All right, so what is the purpose of a notch filter found on many HF transceivers? Okay, so let's say that you have a signal that looks like this, that you're listening to somebody talking and you get a signal, which is somebody laying down a carrier signal right there where that red dot is. So you may be able to implement a notch filter, which reduces your receiver gain right there, essentially making it so that that range of frequencies is no longer there. So let me make sure. Is everybody back? Hello, hello.
Yep, we're back.
Hello.
Hello.
All right, just want to make sure everybody's back. I see a lot of Sunday morning black screens, so you know. All right, so a notch filter allows you to not listen to one particular thing, which has great benefit, which is because I didn't want to listen to it in the first place, and now I don't have to. Okay. Which of the following is the purpose of an IF shift? Okay, so as we derive what a radio looks like, a receiver, because we're doing some receiver design, basically looks like here's your antenna, and here's an RF amplifier, and here's a local oscillator. This is our intermediate frequency. This is a mixer. And then we have a filter, bandpass filter. We take that, we run that through another local oscillator, and we have another IF, and we have another filter. And then we have a product detector, and we have another local oscillator, and then we have this coming out as audio. So this would be like a 3-stage receiver. So if these filters line up, what we end up with is the filters lining up bandwidth wise. However, we can take one of these filters and we can change what the position of the filter. For instance, like this, we just slid this up this way. Now, what do you notice about the intersection of the filters? It goes from here to there, and this other one goes from here to there. Where's the intersection of these guys? Right in here,
Yeah.
right in there. So what we've done is we've done something called an IF shift, which is an intermediate frequency shift, and changed where our filters are working. The benefit of doing that is that this allows us to, let's say we had interference on this frequency right here. This allows us to basically block out the receiver's ability to listen to the interference on that frequency. We've essentially moved the filters and their frequency response in a way that it basically blocks it out. That's known as an IF shift. What is one reason to use a transmitter, to use an attenuator function that's available on transceivers? So it might be that a nearby signal is really, really loud. If it's really, really loud, what can happen is that signal that's really, really loud might be so big that it actually desensitizes your receiver. And if it desensitizes your receiver, then it might actually impede your ability to actually hear what you're wanting to listen to. So the attenuator function actually reduces the gain of the receiver. It puts an attenuator pad of, let's say, 10 decibels in your receive path and reduces the strength of the incoming signal so that your receiver can still work.
Attenuate, to make or become
attenuates.
thin, to
Yep.
make or become thin or weaken.
There you
Yeah.
go.
Thank
Okay.
you, Merriam-Webster.
Yes.
Google will never replace you, my dear friend. Never.
All right, how does a noise blanker work? Okay, so if I were looking at in time, I have, let's say I'm in a car and I have a pulse train, pop, 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 caused by my alternator or caused by spark plugs or caused by something, but it's a periodic pulse train, which has a frequency of, let's say, 300 hertz. It would actually sound like that. Or if it was slower, let's say it was at a period of, at a frequency of, let's say, 20 hertz, or let's say 120 hertz, that would actually be annoying. Well, if you could actually tell that it was a pulse train, a noise blanker is designed to automatically tell your receiver that when this period comes, I want to take the gain of my receiver and do this with it, and automatically knock it down so that the impact of those pulses is diminished. And that would be a noise blanker. Unfortunately, what happens when that happens to the signal that you're actually listening to? It is also dropped down because your receiver is turned down at that point. The gain of the receiver is turned down. So if your noise blanker if you crank your noise blanker or noise reduction way up, so that would be like a noise reduction control or noise blanker. If you crank the function way up to blank this out, it also takes your signal with it, and your signal that you're listening to can end up sounding distorted. The purpose of an electronic keyer. I happen to have one right here, which I use for demonstration purposes for the Morse code classes I teach. This is a code paddle, which sends dits and das. And over here, I have an electronic keyer. The purpose of this electronic keyer is to receive input from this thing, dits and das, and create dits and das, which my transmitter can then use without me having to send with a straight key. So that is an electronic keyer. What's one advantage of selecting the opposite or reverse sideband when receiving CW? What is CW another word for, everyone?
Continuous wave.
Morse code, continuous wave. When receiving CW signals on a typical transceiver, well, okay, if I draw this band right here, and let's say that I have a Morse code signal that I'm listening to, and I get a bunch of interference up here, but it's relatively quiet down on the other side. These signals over here are basically non-existent. So believe it or not, your receiver, even if you're on Morse code, it has a sideband. It's either listening on upper or lower sideband. So if I were listening here, here would be my 0. That would be upper sideband. What would I hear in addition to my Morse code signal? I'd hear all that other stuff, right? Now, if I were to go to reverse and listen to this side, what would I hear?
Everything below that frequency.
And there's nothing below it to hear, which basically means that I have now eliminated the source of interference. It's not bothering me anymore by switching to the opposite sideband. Because Morse code, it doesn't care what you're listening to. It doesn't care if it's on upper or lower sideband. Okay, what is normally meant by operating a transceiver in split mode? So let us draw our frequencies, and we have a signal that we're listening to on 7.020 megahertz.
That's semi-duplex operation, yes.
Yes, this person is transmitting on 7.020, and it says, and we'll also say listening 3 up. Okay, that would mean that when I transmit, I want to be transmitting on approximately 7.023 megahertz. So what I would do is I would put my radio in split mode so that I'm receiving on this frequency and transmitting on this frequency. The other station would be doing the exact opposite. And that would be known as a mode called split. And that's used for split operations. And again, Matt, as you were saying, the advantage of doing so is that if there are, let's say this is what we call a de-expedition station, and they're transmitting from, as they are right now, Lesotho, which is a very rare country to ever hear on the air. Well, they might be hearing, if everybody was calling on that exact same frequency, it would obliterate everyone's ability to hear this station. So what they'll say is listening 2 to 3 up, and they'll say, okay, pick a frequency between 7.022 and 7.023. And I will listen through those frequencies and pick somebody to talk to. If it's a really big de-expedition and they're getting called a lot, they might say listening 2 to 10 up, in which case might be all the way up to 7.030. And you'll basically on a waterfall display see a brick wall of signals. Their job at that point is to listen through that brick wall and pick one, which is really nice that they can actually do a nice narrow band receiver and pick out just one to work at a time. Makes it very challenging to talk to them, but it's worth it. And okay, and that's known as split mode. Which of the following is a common use for the dual VFO feature on a transceiver? So 2 VFOs. A VFO is variable frequency oscillator. So that allows you to listen to 2 different frequencies, potentially at the same time, because you have 2 oscillators, basically 2 receivers. What is likely to happen if a transceiver's ALC system is not set properly when transmitting AFSK signals using a single sideband mode? Okay, so we are transmitting a signal using AFSK. That's audio frequency shift keying. So let's just pick a mode where we're transmitting signals in this range, and they will pick a certain frequency within that range. And they'll shift over time. So we'll send this one, then this one, then this, and this, and this, and this over time. Okay, if you have your ALC not set properly, what will happen is that your audio signal can drive these signals so hard that they actually cause a signal to be put out here and here and here and here as well. So basically you'll get splatter.
Called overmodulation?
Yep. That is
Okay.
basically overmodulation, and you'll cause spurious emissions, which will piss off everybody else on the band, because you're sending out, power that is just going to be, let's say there's people making contact down here. Well, and some others making contact up here. you've just interfered with them because your ALC is set too high. You're overdriving your transceiver. Okay, which of the following can be a symptom of transmitted RF being picked up by an audio cable carrying AFSK? Okay, so that means
Hey,
that,
Scott,
yes,
Scott, so how do you know your ALC is too high? And what is
there's an
that?
ALC, every transceiver has a meter that says ALC. And it's, if you have a multifunction meter on your transmitter, one of the options is ALC. When you're transmitting on a digital mode, you typically want to see ALC almost never activated. Usually it'll be like on the same scale as your power meter, but it'll say ALC. You typically never want any action when you're transmitting, because that's literally automatic level controlling. That's saying that the transmitter circuits are automatically limiting what's going out because the incoming signal's too loud. Okay, let's see. If you have RF on your cable, you might have a distorted transmitter signal. If you're making digital communications, essentially your digital communications will be distorted and no longer functioning, and you'll have connection timeouts. Let's say you're using WinLink, WinMore, Pactor, any of those digital modes, it can drop your connection. And also your Vox circuit can actually get stuck and leave your transmitter keyed up. In other words, the RF is causing a feedback loop, and the RF is actually holding your radio transmitting, which causes the radio to transmit, which keeps the feedback loop active, which causes the radio to transmit, and so on and so forth, and it can never drop. Okay, what is the correct adjustment for the load or coupling of a control of a vacuum tube RF power amp? Okay, so we're going to draw our power tube once again. Here's our grid. Here's our plate. We have electrons flowing across. What happens if we have, this is our plate. What happens if we have too much current flowing out of here? What will happen to this element?
It'll overheat.
It'll overheat and it'll destroy your tube. So what you typically want to do when you're adjusting the output of a circuit that's running off of a vacuum tube is you want to maximize the power output and keep the plate current below the maximum limit. So peak the load, or peak the load, dip the plate. Peak the load, dip the plate. If you've ever set up a tube amplifier, that's the thing you normally do. You peak the load and you dip the plate, because you always want the plate current to be below the maximum. On an old Kenwood TS 520S, you can look up, your plate current would typically be a max of about 200 milliamps at 800 volts. And that would give you 150 watts, 160 watts input. But notice, it's only 200 milliamps, right? But it would operate at 800 volts power supply. So you do E equals I times R, P equals I times E, and you get roughly 160 watts, which would give you about 100 watts output because of the efficiency. If you keep this below 200 milliamps, you won't destroy your tubes. What is the reading on the plate current meter of a vacuum tube amplifier indicating correct adjustment? Peak the load, dip the plate. So you want to see a dip on your plate. And I don't care how you remember it, just remember you always dip the plate. And this is plate current. You want to peak the load and dip the plate. What's the reason to use an ALC control with a power amplifier? There's actually sometimes when ALC is good, because if your signal is too big, it can overdrive an external power amplifier, which can actually damage the amplifier. The ALC prevents that from happening. Again, if you're running digital, what function does too much ALC do? It causes
Um,
distortion.
Easier transmitter keeps it open.
Right. Well, no, it causes distortion.
So
So
Not microwave.
basically what that means is you don't want your ALC to be active and you don't want your ALC to not be active. So basically what that means is you want to set it so that you have a nice clean signal and that your drive is such that it's still not overdriving your amplifier. What condition can lead to permanent damage to a solid state RF amplifier? Excessive drive power. So essentially, let's say that your external amplifier, it requires 10 watts of input to produce 1200 watts of output. Well, what happens if you feed 50 watts into it? You forget and you turn your power up to 50 watts. This is a transistor amplifier. What would happen if you drive too much into it?
Pop.
You let the smoke out. And everybody knows that smoke is the electronic component that makes every electronic component work. It's the magic stuff. If you let the smoke out, it doesn't work anymore. So don't let the smoke out. Does everyone knows that, right?
Yep.
Smoke is the magic stuff that every electronic component has the smoke inside it. That's what makes it work. If as soon as you let the smoke out, it doesn't work anymore. Ergo, it must be that you let the smoke out. And that's why it isn't working.
Makes perfect
sense, doesn't it? So don't let the smoke out. Why is a time delay sometimes included in a transmitter keying circuit? And that is to allow the receiver to completely switch over, because you have this thing in a transceiver called a transmitter and a thing called a receiver. And then you have a TR circuit and they use the same antenna. Well, when you switch over from receive to transmit, what happens if the transmitter switches over before the receiver's quieted down? The path goes like that, and your transmitter sends all your power directly into your receiver, which will cause what to be let out of the receiver, David?
The magic smoke will be let out.
Magic smoke, and it will no longer work. So that's why we have a.
I'm curious if you can you generate like a new source of this magic and then take a bricked radio and just stick it in the smoke?
You can't. It comes from the factory that way.
Okay.
It comes with the smoke included from the factory, and once you let it out, you can't put it back. What type of device is often used to match transmitter output impedance to an impedance not equal to 50 ohms? So I have my antenna here, and I have my transmitter here. What is this thing called?
Antenna tuner.
That is called an antenna tuner or an antenna coupler. This is an impedance matching device. Okay, next. When you set up your oh, that's annoying. When you set up your, okay, we're on to page 61. When you set up your amateur radio station, sometimes called your shack, you'll not only want to acquire radios, but also some test equipment. That is true. What is the advantage of using a digital voltmeter compared to an analog voltmeter? Which is more useful to you? To see a meter with a bunch of graduations and something that goes across a display, or to say 3.26 volts DC?
Digital voltmeter is
the digital
not
voltmeter is
peak.
more accurate. Yes, it'll give you more precision. Not necessarily more accuracy, but it'll give you more precision. Why is high input impedance desirable in a voltmeter?
Front loading.
The main reason being that if I'm trying to measure something like this, and here's a circuit that's live, and I put a voltmeter right here, ideally, how much current does that voltmeter draw? How much energy does it take to run? The more it takes, the more it affects the circuit itself, because you can't observe something without changing it, right? So the less current this thing pulls to measure it, the less it affects the actual circuit that you're testing. because E is equal to I times R. R is equal to E divided by I. So if your resistance is very high, that means that you will have very little impact on the circuit itself. So you want your voltmeter to be really, really high impedance. And that's usually measured in a term of like ohms per volt. And you would want this to be at least something like 20,000 ohms per volt. So really high impedance. Let's see. What is an instance in which the instrument with analog readout may be preferred over an instrument with digital readout?
You're tuning an antenna.
If you're tuning an antenna, that's right. So if I have my antenna tuner and I have a meter that goes like this, and I'm tuning a tuning knob over here, around and around and around, what I want to see is this is normally here, and then I see a sudden dip. I don't really care exactly what that value is. And then I might see it go up slightly, and then I want to see it go down again, and then up slightly, and then I want to see it go down again. So basically that'll tell me if I had to actually interpret what a digital meter was saying, I would have to interpret it. In this case, it's just a visual indication. So if you're tuning a tuned circuit, this is a much better way of doing it, which is why most antenna tuners actually have a meter that looks like this with a single needle, or sometimes even a double needle. Sometimes they'll have one that goes like this and one that goes like this. And where they cross, that tells you something. That actually gives you the standing wave ratio. Okay, what type of test equipment contains horizontal and vertical channel amplifiers? That can actually give you a picture of a waveform.
An oscilloscope.
An oscilloscope. This is your time axis, and this is your voltage axis. The nice thing about an oscilloscope versus a digital voltmeter is that complex waveforms like this one can actually be seen and measured. You'll typically have a set of blocks on the display that gives you a time base and a voltage difference. Like here's your 0 line, and that can tell you that, okay, this was my peak. Here's an approximate value. Here's my, and it occurred over this period of time. So what's the best instrument for checking the keying waveform of a CW transmitter? Again, CW is another word for
continuous wave, Morse
continuous
code.
wave or Morse code, which is what we use. So to be able to look at the waveform of a CW transmitter, you'd basically do this, and you'd see this. So here's your envelope, and this is what your rise time looks like, and then your fall time. And that will basically give you a nice picture of what your Morse code signal looks like. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? You'd actually pick off a small sample. This is a very high impedance reading on your oscilloscope so that it doesn't affect anything too much. You'd pick off a small sample and display it on your screen. So attenuated output of the RF transmitter. If you're looking at an antenna analyzer is a substitute for your transceiver. So let's say that you have your antenna system, and here's your transmitter right here, and it's also a receiver. To verify what your antenna looks like, you would actually take this away and replace this with an antenna analyzer. And what that is a wideband, very low power transmitter and a receiver built in. And what it does is it actually looks at the energy that comes back. And if it's a meter, it'll say, here's your SWR, and here's your resistance. Sometimes, if it's a nice graphical one, it will actually scan a range of frequencies like an oscilloscope does, and it will give you an SWR plot that looks like this. and it'll say, here's your minimum at 7.206 megahertz. And it will give you, say that your minimum is 1.3 to 1. And it'll say, okay, well, if you want, basically you can then interpret this and say, okay, if I want to tune it lower, the antenna is too short. If I want to make it higher, the antenna is too long. So it can tell you a lot. So basically that requires that you leave the antenna and feed line connected, and it replaces your transceiver. What's it used for an antenna analyzer other than measuring the SWR of an antenna system? Some of them can actually measure the impedance of it, determine the impedance of a coaxial cable. By taking it and hooking it up to it, you can actually measure a cable's characteristic impedance. What problem can occur when making measurements on an antenna system with an analyzer? Well, because what is an analyzer? It's a transmitter and a receiver. So let's say there's somebody else nearby transmitting on a frequency that you're scanning. All of a sudden, this thing actually receives it and says, whoa, it's really big. So a nearby transmitter that's transmitting at high power could actually affect your transceiver. Most people never encounter this problem, to be honest. Which of the following can be determined with a directional watt meter? We covered this a little yesterday. We have forward and reflected power going up to an antenna. So if we measure the forward power and the reflected power, we can calculate our SWR from it, or standing wave ratio. Which of the following instruments can be used to monitor relative RF output when making antenna and transmitter adjustments? That would be a field strength meter. Literally, a field strength meter is kind of like a watt meter, except that it's a watt meter that's connected to a little piece of wire, which acts as an antenna. And then it has a watt meter or a voltmeter hooked to it. The more energy that this thing picks up, the higher the reading on this meter. That means that the field strength is bigger. What can be measured with a field strength meter? So let's say that you have an antenna up here and you walk around the antenna and you plot out what your field strength is. Well, that gives you a good idea. If it's strong here and weak here, if it's strong here and strong here and strong here and strong here and strong here, you know more or less that your antenna pattern looks like that. So you can plot it out. So you can look at the radiation pattern, at least in the near field. What type of transmitter performance does a two-tone test analyze? That's basically taking two non-related frequencies and putting them into the transmitter and seeing how much mixing you get. Ideally, in an amplifier, you have this range called, this is cutoff. What's the upper range called? Saturation. What's the area in the middle called?
Linear.
Linear, because it's in the shape of a line. So this frequency, this signal, they should be at certain frequencies. And ideally, when they go through this amplifier, if I have a tone of 300 hertz and a tone of 1000 hertz go into it, what should I get out? 300 hertz and 1000 hertz, right? So if I get some other stuff, that is indication of the transmitter of the amplifier not being completely linear. So these two non-harmonically related audio signals are fed into it, and I measure how much other stuff comes out. That gives me a representation of how linear my amplifier is. Okay, what sound is heard from an audio device or telephone if there's interference from a nearby single sideband transmitter? That would be something like this. If anyone's ever heard, has anyone been around long enough to remember a wired telephone? Okay, what does a wired telephone have connected to it?
Wire.
A wire. Any piece of wire functions as what?
Antenna.
Antenna.
That's right, which means it picks up RF and feeds it into the telephone. So essentially, if you're transmitting with single sideband and a telephone picks it up, what you're going to hear is, which is the same thing that my parents used to hear from me on their stereo system. It came through the speakers without the stereo even turned on. Yep.
What wattage were you transmitting at, man?
Oh, 50 watts. But it was inside the house. The antenna was
Okay.
inside the house. All right.
Yeah,
What is the effect of an audio device when there's interference from a nearby CW transmitter? Well, when it's on, you won't hear any distortion, but when it goes on and off, you'll hear by clicking and humming. Which of the following might be useful in reducing RF interference to audio frequency devices? Well, you want to get RF off and you want to pass low frequencies. So if I have something that is in and out, I have two wires going in and two wires going out. What would I use to allow radio frequency energy to go from this wire to this wire? What device passes really, really high frequencies as though it's not even there?
A capacitor.
Capacitor. It blocks low frequencies, or it allows low frequencies to pass and allows high frequencies like radio to go this way. So that would be a filter capacitor known as a bypass capacitor, which you can use on your power cord, believe it or not. And it always seemed weird that like you could actually, if you had interference on a TV, that you could hook a tiny little disc capacitor across the power line of a TV. And this disc capacitor, let's say, was rated at 300 volts. That's absolutely fine. Essentially, it would never blow up because it was only 120 volts AC. And what's the peak voltage at 120, everybody?
170.
About 170 volts peak. Well, this capacitor is fine for that. And it takes all the RF and sends it down and sends it back to where it came from. Doesn't allow it to get into your TV. Okay, what to the following would reduce RF interference caused by common mode current on an audio cable? We saw one of these yesterday and it looks just like this. Can everybody see the little picture of me?
Yep.
That is a ferrite choke. Basically, if there's current on the outside, that makes a magnetic field. The magnetic field will get sucked up by the choke. And yes, the choke gets warm, but there's probably not enough energy to worry about it. And a ferrite choke is also usable on a piece of coaxial cable to keep energy flowing down the outside of your conductor back into your station. Because here's one thing that I'm going to put here. Okay, so here's my coaxial cable. All right, how many conducting surfaces are there on this coaxial cable? There's not two. How many are there?
Three.
There's three. And the reason there's three is because of something called the skin effect. DC current, if I were to draw a cross section of a wire, DC current distributes uniformly throughout the wire. AC current does this. It flows on the outside. The higher the frequency, the closer it flows to the outside. There's nothing on the inside of a conductor. So that means that at AC, what we have is surface number 1 on the outside surface of the center conductor. Surface number 2 is on the inside of the shield, and surface number 3 is on the outside of the shield, and they're all separate. So typically 1 and 2 are going to be equal and opposite. 3 can be anything else. So what we do is, because 1 and 2 are opposite each other and are isolated from the outside, we would put a ferrite bead or a ferrite core around the outside of it. And if there's anything on the outside of the cable this would basically absorb the energy from that. So we might have RF over here as it's traveling this way, and we're happy face on this side.
What's the difference between just putting a ferrite clamp around it versus wrapping the cable around?
Okay, so if you take a ferrite bead that looks like this, right, hollow bead, if the hole is big enough, if you pass the cable through one time, you'll get a certain amount of attenuation based on the cable. If you can do this and wrap it around it, and wrap it around it again, and wrap it around it again, you actually get a multiplicative effect. It's not additive, it's actually multiplicative. So if you can wrap it around it multiple times, like 4 times around is like 16 times better than once. And that's why you would do that if you can.
Hey, Scott, when's your next break going to be? Do you know?
It's going to be in about probably 20 minutes.
Okay.
Okay, let's see. How can a ground loop be avoided? Okay, so let's say I have everything. I should really use green for this because green is ground. So let's say I have all of my equipment tied together like this. And then I have something that goes like this from here to here. All right, does anybody see a problem with this? Does anyone see a roundness?
Yeah.
Circulation. You can actually have current that flows around this loop. All right. What's a wire? Man, what's another name for a wire in our case?
Antenna.
An antenna, yeah. That also can mean that we can have different levels of potential or electric voltage at different points in this loop. So this is known as a ground loop. And a ground loop can radiate RF and it can put things at voltages you didn't expect. So in order to fix that, what we would do is go like this. Connect everything with its own leg to a single point.
Yeah.
Okay, what's a symptom of a ground loop somewhere in your station? You get a report of hum. It could be picking up a nearby light. It could also be picking up RF. If you get hum on your signal, that can be a ground loop. What effect can be caused by a resonant ground connection? We were just sort of talking about that. Let's say you're grounding wire between here and here. That's your ground stake, is 66 feet long. And you're operating on the 40-meter band. Or let's make it the 40-meter band. On 40 meters, that's 132 feet. 66 feet is a half wave. A half wave is a really good what? Really good antenna, yeah. All right, so now let's actually go to the 80-meter band, and that's 264 feet long. And now that half wave is a quarter wave. Okay, if we were to draw this voltage here, what we'd find is that it would be 0 here and high here. Well, how can we have high voltage here at the end? It's grounded. We can't, can we? So I drew this wrong. What this really means is we have 0 volts here and high voltage right here, which basically means it's not high voltage in that it's unsafe, like you're going to get 120 volt shock. But what this is you've got a high RF voltage right here. So you might have, if you're transmitting with a few hundred watts, you might have, let's say 200 volts RF on the case of your transceiver, which you think is grounded. Well, is it grounded anymore? It is for power. It's connected to this ground, so you won't get an electrical shock, but you could get a really nasty RF shock. I learned this firsthand, again, when I had a 2nd story station connected to the water pipe in the house. Who knows how long it was to get down to the actual ground. And I leaned up to transmit, and it was a Kenwood MC50 microphone with a metal cover. And I leaned up against it, and as I started talking, I got a zap right on my lip. It really hurt. Basically, that was because the radio was not at RF ground. So you can get high voltages on the enclosure.
So how do you RF ground it?
You go with a really short cable to ground, or you tune it out of it. And the way you would tune it out of it is you could do something called an artificial ground, which uses a really short wire and a counterpoise wire of some length. And this is like usually an artificial ground box, which is basically an antenna tuner, except that it tunes this wire. It tunes that wire and that wire so that this might be at high voltage, and this is at 0 volts now. What that really means is you basically have an RF current meter that looks to see what your current is, and you basically peak it so that you get either high or low current, and that tunes your chassis for 0 volts. It also means don't touch this wire over here, because it's probably carrying some pretty high voltage.
So you connect that to your ground wire to your
No.
radio.
You
and
typically
then-
don't. You could connect this to ground, or you can just leave it hanging, like stick it out the window.
Huh.
Impedance matching. Okay, so what can be the problem if you receive an RF burn when touching your equipment while transmitting on an HF band, assuming it's connected to a ground rod? That would be the ground wire has a high impedance on that frequency. In other words, you're at a high voltage point. Why does the metal enclosure of every piece of station equipment need to be grounded? It ensures that hazardous voltages, we're talking about, 800 volts power, to be not on the chassis. So if you touch it, you won't get electrocuted. An RF burn won't electrocute you, but it'll really sting. 800 volts with current behind it will kill you. 120 volts with current behind it will kill you. What technique helps to minimize RF hotspots in an amateur station? If you bond all your equipment together, that basically means you don't have ground loops. So all the stuff gets grounded together. Which of the following could be a cause of interference covering a wide range of frequencies? An arc, like a lightning strike. Lightning strikes are AM. They produce, if I were to draw a frequency spectrum from 0 to infinity, a lightning bolt is basically a square wave. A square wave puts out energy at literally all frequencies of diminishing value. But basically a square wave puts out just a blanket of energy, which is why it doesn't matter what you're tuned to. If there's lightning nearby, you'll hear it on AM on all frequencies. So what does that mean? That means if you have an arc is basically a lightning strike. And if you basically hear a snap, crackle, or pop on any frequency, that means look for arcing. Which of the following is an advantage of a receiver? DSP, IF. DSP is digital signal processing. IF is intermediate frequency. So if we're building our receiver, that means that we again have our signal chain that goes from an antenna to an RF amp to a mixer with a local oscillator to a filter to another mixer to your speaker. If this is done with DSP or digital signal processing, that means that instead of physical filters, you have a computer chip that is doing sampling of that signal, turning it into a string of digital signals and processing it using digital processing. What that also means is that you can actually use your computer that's inside there to create different filters. So The benefit of that is that you can actually have a filter that looks like this, or you can do this and make it more sharp. You can change the roll-off frequencies. You can have one that has a wider bandwidth. You can have one that has a bandwidth that looks like this with a big notch cut out of it. And that's all done digitally by computer. The fact that you can program it to do that. Okay, we're into speech process. Yes.
So in the digital signal processing, excuse me, was it all analog in before you, but you had to have an ADC to
Yes.
then?
Correct. You went from analog, and then you went through an analog to digital converter, did all your processing, and then probably turned it back to analog for sending it out.
So, I mean, if you go through your ADC, why wouldn't you just like go straight to a sound card or something like that and just
You can.
strictly?
You absolutely can.
Okay.
Yeah, but if you want to play through a speaker and you don't have a sound card, you would basically run it through a D to A converter and turn it back to analog and pump it through your speaker. You can also, typically those sound levels are going to be really low. You know, I mean, it's digital. So you'd want to convert it into something that could actually drive a speaker through an audio amplifier. But yeah, if you have a sound card, there's no reason you couldn't do that.
So why not just start at the very straight from the antenna, go straight to an ADC and then, you know, onto a sound card?
That is called an SDR. That is a software-defined receiver where everything is done digitally.
That seems advantageous.
It is advantageous, but it required new technology which didn't exist because it had to operate fast enough. Because if we look at what's coming down from an antenna, let's say that we're looking at 50 megahertz. How fast do we have to sample that to get a good digital representation? What's our sampling rate? Sampling rate has to be 2 times max frequency. That is the minimum sampling frequency that you need. And in fact, it's actually 2.2 times or greater. So which means that if we want to be able to replicate 50 megahertz, how fast do we have to sample?
Let's see.
110 megahertz, which means we have to sample it 110 million times every second. And let's say we want 16-bit resolution. So every 110 million times per second, we download 16 bits indicating what the signal level was. So we take 110 million times per second times 16 bits. What's our bit rate? It's about 2 gigabits per second. It took a while, first of all, to come up with computer chips that could run that fast and download that much information. Then what do you have to do with this? You have to actually process the damn thing, which means you need a processor that not only receives that much information, but can also work with it and filter it and run it through actual, you know, algorithms and come up with something that looks like what you want it to. And then what do you have to do with it?
Display it.
Convert it back to
Display it
analog.
or run it through a D to A converter that puts it out through a speaker so you can listen to it. How long can this take? Realistically speaking, if this is a functioning radio, how long can this take?
Split
Well, it
second.
has to happen really fast.
Yeah, I mean, this whole path might take a tenth of a second for all that processing to occur, and all of this data has to not get stuck in a bottleneck, which means you need a massively parallel system to handle this amount of data, which is why it took so long for us to actually have something that was a high frequency functioning SDR. The ICOM 7300 is one of the first commercially available, relatively cheap boxes that implements this. I mean, this is $1,000 or less.
Okay. Okay, yeah, that's what I was, my next question. So practically speaking, price point, the technology is just starting to arrive there.
Correct. But it's an amazing thing, because if you look at all the stuff that this eliminates from the chain, it eliminates intermediate frequency amplifiers. It eliminates mixers. It eliminates crystal filters. There's essentially some really, really fast computer processing taking place that replaces a lot of mechanical hardware. Excuse me. So yeah, there you go.
Cool.
It took that long for the technology to get there. The ICOM 7300 is the perfect representation of that technology. There's also numerous other ones out there. Everyone's moving toward digital processing because of its incredible flexibility. Okay, so speech processors, S meters, etc. What's the purpose of a speech processor? A speech processor can increase the intelligibility of a transmitted phone signal in poor conditions, and it does this by enhancing certain frequencies and doing some filtering that basically makes your signal have more punch as other people try to hear you. What describes a speech processor and how it affects a transmitted sideband signal? It increases average power. Again, it enhances certain parts of your speech and gives it more punch. It increases the average power in doing so. If your speech processor is turned up too high, you basically sound like this, and then nobody can hear what you're saying. So it's important to actually have other people listen to what you sound like and determine whether or not they can actually understand what you're saying.
So does that affect ALC?
No. If well, no, ALC, yeah, they're sort of one and the same. But that the ALC will work on what you're actually sending. The speech processor determines how much you're overemphasizing things. So they kind of work together. But basically, if your speech processor's turned up, you'll hear all the background noise and your speech will be distorted and splattered all over the place. And you can hear this if you listen during a contest. You'll hear somebody with their speech processor turned way, way up, and they'll just sound like this, and they'll say, November 7th, and they won't be able to tell one letter from another. So they're basically trying to replace one problem with something and causing other problems.
So, I have a 7300, but I don't remember there being a speech processor on it. But
oh yeah, there is. It's called compressor. It's called COMP. And it has a level, you turn it on and off, you go from 0 to 10. And if you monitor your own signal through your headphones, you can definitely hear the difference. And tonight, when we're on the 10 meter, on the schmooze thing, turn it on and off and ask other people to listen to you and tell you which way you sound better. If you don't need the processor, you typically sound better without it.
So there's a difference between mic gain and compression.
Yep. Compression is literally like compandering. If you think back to Dolby audio, that's sort of like what a speech compressor does. The Dolby compression mechanism. It emphasizes certain frequencies to make it more powerful. All right, where is an S meter found? An S meter is found in a receiver. It will literally say S, which stands for signal strength, and it will say 0, 1, 3, 5, 7, 9, and then plus 20 dB, plus 40 dB, and so on and so forth. And the needle will basically start at 0 and go over. S meter measures received signal strength. 1 S unit is roughly 4 dB. Or sorry, that's not right. 1 S unit is roughly 6 dB, which is 4 times the strength. So basically, if you go from S2 to S3 is 6 dB. If you go from S8 to S9 That's 6 dB. Right? If you go from S3 to S9, that would be, let's see, 24, sorry, nope, 36 dB, because every S unit is 6 dB. So you could actually figure out, if I crank up my amplifier, what the other person should see as a difference. So if I put on if I put in a 20 dB amplifier, let's say I go from 1 watt to 100 watts, that's 20 dB. The other person should see an increase of about 3 dB, or sorry, 3 S units. So if I was S3, I should jump up to an S6. Okay, how does a signal that reads 20 over S9 or 20 dB versus S9, how many decibels stronger is it?
20 decibels.
20 decibels.
100
20 decibels is 10 plus 10, which is 10 times 10 is 100 times stronger. So 20 decibels over S9 versus S9 is 100 times bigger. Okay, how close to the lower end of a phone segment should your displayed carrier frequency be when operating on lower sideband? Okay, so here we go, 7.125. You hear this all the time during contests. People scraping the edge. Okay, so here's my carrier frequency at 7.128. If my signal is 3 kilohertz wide, where is the bottom end of it?
Right there at the limit, but slightly before, because it's not quite 3 kilohertz.
Right. It basically, what this means is that's the lowest dial frequency you would go to and maintain your signal above 7125. So you want to keep your signal on lower sideband, 3 kilohertz above the band edge segment. Now, I heard this yesterday as well, 14.350. There was somebody on 14.349 running upper sideband. Where does the signal end?
Outside the ham bands.
Outside at 14.352. That signal is illegal, along with that of everybody else who's replying to him blindly, because he's calling CQ contest. People are answering him. Every single one of them is transmitting an illegal signal. That's a good way to get a nastygram. The FCC used to do it. Now, if you, it'll typically be from a volunteer monitor who does it and tells you, hey, you know, if you continue to do this, the FCC might send you a nastygram. So if you're transmitting on upper sideband, you want to be 3 kilohertz below the upper edge of the band. So in fact, this is the last question on page 67. What frequency range is occupied by a 3 kilohertz USB signal when the display says 14.347 on upper sideband? And that would be up to 14.350. So it covers this entire range. And that is why when you're operating, you want to stay inside the band, and that's how to do so. All right, everyone ready for a 5-minute break again?
One quick question. How do you know they're transmitting on upper sideband?
Because if you are listening on lower sideband and you can hear them, then they're transmitting on lower sideband. You can't listen on the wrong sideband. If you have your receiver on the wrong sideband, it'll sound, basically the speech will be inverted. All the frequencies are backwards. You can also, if you have a waterfall display, you can see their signal. I mean, you can see that it's outside the band.
10 megahertz. That's the margin, right?
On what?
Everything below 10 megahertz is lower sideband. Everything above 10 megahertz is upper sideband.
When using voice, yes. But when using digital, no. Actually, on digital, the de facto is upper sideband for everything.
And 60 meters is also upper sideband. Yes?
60 meters is also upper sideband, even on voice.
Okay. There we go.
Yep.
Okay, breakfast time. He's reading stuff out of the book and answering the questions, and I don't have the book, so I try to write the question down and then answer, and it goes way too fast. So, oh, look at you. I like being out here.
It's a nice place, isn't it? Yeah, it's just.
I'm gonna put us on mute so they can't
DC is underwater. What? Washington DC is underwater. Having coastal flooding.
Okay, you all. Let's keep going.
The upper and lower sideband across the handband, is that written in law, or is that just by convention?
That's convention. The only one where it is written in law is the fact that we have access to the 60-meter band, which is a shared band with the military, and we are required to use upper sideband.
Okay, yeah, I knew about the 60-meter, but I wasn't sure about the handband.
Yeah, everything else is it's just convention. All right. We are on 68, continuing right along into HF mobile radio installs, emergency and battery power. So before we do that, do we have any questions on the last couple sections? Everybody been taking practice tests? It's kind of at your own speed, but hopefully they're making more sense.
My practice tests had a major up spike after yesterday's class, so it's making good progress.
Good. All right, here we go. HF mobile radio. Which of the following direct fuse power connections would be best for a 100-watt HF mobile installation? That would be going directly to the battery using heavy gauge wire. What's nice about it is that we don't trust the car's frame. We don't trust the vehicle frame as a good ground because it's not necessarily. It's usually okay, but we don't really want 20 amps we don't want 20 amps going back through it. We go back to the battery with 20 amps. We pull 20 amps. We don't pull it from the circuit. We don't pull it from the cigarette lighter because it's not designed for it. Why is it best not to draw there we go. Why is it best not to draw DC power for a 100-watt transceiver from the auxiliary power socket? And that's like the cigarette lighter, and that's because it isn't designed for it. Can't handle the current. Which of the following may cause receive interference in a radio installed in a vehicle? Can be the vehicle charging system, the fuel delivery system, or the vehicle control computer. I've heard all of the above. Which of the following most limits an HF mobile installation? That would be the antenna system. It is really easy to build a really bad antenna system. What's one disadvantage of using a shortened mobile antenna as opposed to a full size? Well, it's always a compromise if it's short. If it's shortened, basically what you have is a very, very low feed point impedance, which means you need a transformer to transform down to that impedance. The other thing is that your bandwidth might be really, really small. So if you do achieve a match, you might have an operating bandwidth if you don't have a tuner of some kind or the ability to change the antenna length. You might have a bandwidth of, let's say, 20 kilohertz, which might mean, okay, well, for certain things, that's fine. But if I want to operate from, let's say, 7.125 on the 40-meter phone band up to 7.300, and this is my SWR curve for my antenna, and it looks like this. Here's my good band. All right, 7.185, 7.205. Well, what about all these frequencies out here? Well, that would be known as a compromise because that's what you get. So you might actually have two different antennas, which you can unscrew, put a different one in, and that other antenna might be cut to give you this band up here.
In that case, you would need a switch box like that one. Yes.
Or you just go outside and unscrew one and hook the other one in to the base. You can also do a screwdriver antenna, which has a variable loading coil in the base which jacks it up and down and changes the length of the loading coil in the base, which changes your resonance, which is why a screwdriver antenna is so great.
What sort of fractional lengths can you run and get those sort of like little windows into a band? Like is it 8th wavelength or 10th wavelength or things like
Well,
that?
it depends. Typically what you're going to do, like a screwdriver antenna is usually an 8-foot whip over a coil, right? And you look at an 8-foot whip on 10 meters, that's perfect. I mean, that's a perfect 10-meter antenna. This will work well on 12, 15 meters, 17, and even 20. You just have to expose more and more of the coil. What happens when you get down on 30, 40, 80, and don't even bother with 160 is that your bandwidths are really, really low and your efficiency is incredibly low. I mean, on 80 meters, you might have, 3% efficiency. I mean, you're still putting something out, but 97% of your signal doesn't exist. But there are plenty of people who operate 80-meter mobile. There's excess gain on other people's antennas that they can still be heard. What's the purpose of a capacitance hat on a mobile antenna? A capacitance hat essentially does this. At the top of an antenna, it adds electrical length to the antenna, essentially giving a place for charge to accumulate and making the antenna appear longer. If you want to see something that looks like this, the other way to do it, of course, is to also add a loading coil. So here's an antenna. This is a very popular antenna, believe it or not. This is called a Texas bug catcher. And the reason that this is called a Texas bug catcher is that this is an open air coil and it catches bugs in it. It's also a very solid, stiff antenna, typically with a loading coil at the top and then a stinger up above it. And this is actually a relatively efficient antenna for 80 meters. It's still not great, but it's a lot better than nothing. And how come the loading coil is up high and not down low?
Structural strength? I don't know.
Nope.
Nope.
Other ones? Here we go. What is my current at the end?
Current is 0.
Current is 0, which means that I'm going to start to draw my current curves like this. Okay. If I put a loading coil here, is my current compared to down here, where is there bigger current?
There's bigger current at the bottom. So
Right.
you want where there's less current.
Because
so you get,
that's right, because the current is what launches the waves. So basically, the closer to the end you can put your loading coil, the more efficient your antenna becomes. And that's why your loading coil up here is way up high, as opposed to at the bottom. Okay, what's the purpose of a corona ball on top of an HF antenna? You're typically going to, at high power, you're going to develop high voltages. The corona ball allows you to dissipate high voltages to the atmosphere instead of from a single point, which actually might cause, an electrical discharge and zap, 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 making RF noise. So it reduces the RF voltage discharge because it's in the shape of a ball. It has more surface area. That's called a corona ball. What's the name of the process by which sunlight is changed directly into electricity? That would be called the photovoltaic effect or photoelectric effect. I believe that was an Einstein thing. We use it for solar panels. It's known as photovoltaic conversion. And a fully illuminated silicon photocell generates a half of a volt DC. So how would you make 20 volts DC out of half-volt cells?
You serialize them.
Put them in series and you would use 40 of them. So there you go. You'd use 40 of them in series. And if you wanted to make more current,
Put them in parallel.
you'd put multiple chains in parallel. So if you look at how a solar panel is built, you'll basically see this on the inside. You'll see that you'll have chains of solar cells and then all those fed in parallel. Okay, let's see. What's the reason that a series diode is connected between a solar panel and a storage battery being charged?
So it doesn't go backwards if it's dark.
It doesn't go backwards if it's dark. That's right. Because you don't want it to go backwards. You don't want to actually run current through the solar panel. So you put a diode in here to keep that from happening. Because suddenly your voltage on your solar panel, which was normally 20 volts, which is enough to charge your battery at night, is now 0 volts. Well, that means that your battery wants to try to backfeed through the panel. That's why you would use it. Okay, next.
Wait, on which side of the battery do you put the diode?
You'd put it on the plus side, and you would, because the solar panel is going to try to feed, here's the plus side, here's the minus. It's going to try to feed that way during the day, which is good. You want to float charge your battery. But as soon as that goes away, this diode will block the current flow from the battery into the solar array.
Okay.
Essentially, if you think of the solar panels as a power supply, this prevents one power supply from backfeeding the other one.
Okay.
But you want to backfeed the battery. That's the whole point. And so
So
that's
you
what it
you
requires.
basically float charge the battery. And if you look at it like this, essentially what you have is, I mean, this is the panel, and this is the battery. And if you have a higher voltage here than here, so let's say this is at 20 volts, and we're going to have some kind of charge controller. So we'll call this 14.5 volts. The battery is nominally at 12 volts. That will cause it to basically charge the battery up to float charge the battery. But then if this is suddenly turned off, this is now 0 volts. Without that diode there, what the battery will see, oh, that's 0 volts. It's going to try to flow current back that way. So by adding a diode pointing this way, that keeps the current only flowing this way around the circuit. What's the disadvantage of using wind as a primary source of power? Without an energy storage system, wind is very fickle. So if the wind isn't blowing, you get no energy. So that's why you need a big battery to charge up when the wind is blowing. Okay, so we are now on page 70. Which mode of voice communications is most commonly used on the HF amateur bands? That would be single sideband. What's nice about single sideband is that only one sideband is transmitted. Well, in your transmitter, upper and lower sideband are made at the same time. The carrier is also made at the same time, but before we amplify it, we filter out the carrier and we kill one of the sidebands with filtering, because there's no point transmitting redundant information. It just takes extra power. As a result of this, we get less bandwidth filled up in the band. How wide is a single sideband signal in kilohertz? 3. It's 3 kilohertz wide. AM is 6 kilohertz wide. And then you also have that carrier in the center, which wastes power. So less bandwidth, greater power efficiency. Which sideband is most commonly used for voice communications on 14 megahertz or higher?
Upper.
That would be upper sideband. So therefore, on the 17 meter, and what I'm going to do is hopefully be able to bring this up. On the 17 and 12 meter bands, what would you use on voice communications?
Upper sideband.
Upper sideband, because they're higher frequencies. And I'm going to bring up this chart here if I can find it. Which of the what's used for SSB voice communications on VHF and UHF? Upper or lower sideband?
Upper.
Upper sideband. Notice it's used almost everywhere. Okay, here we go. And we're going to bring up the Band plan.
It almost seems that like, because USB is so ubiquitous, that it would be easier to learn where the lower sideband is commonly used.
Yep, that's true. So right here, 40, 80, and 160. That's where we use lower sideband. You're absolutely right. 40, 80, and 160. And that's all. So 40, 80, and 160. Those are the only places we use lower sideband. And in fact, which of the following modes is most commonly used for voice communications on 160? Now they call it 75. And the reason that it's called 75 is because the band, the 80 meter, 75 meter band is so big that down here at 3.5 megahertz, the wavelength is 80 meters, and up here at 4 megahertz, it's actually 75. So some people call it 75. Colloquially, it's the 80 meter band, but 160, 75, and 40 meter bands are lower sideband. And there's the answer to that question. Why is lower sideband used on 160, 75, and 40 meter bands? There's no good reason, really.
It's just a convention
convention.
you all adhere to, right?
It's convention. Yep. Good amateur practice because it's convention. Who should respond to a station in the lower 48 who calls CQDX? Okay, so CQ means
someone outside the United States.
right. Because CQ means I'm looking for somebody to talk to. DX means outside of where I am. So somebody in Europe calling CQDX would be looking for somebody who is not in Europe. Okay, what's the way to break into a phone contact? Just like on single side, just like on the 2 meter repeater, how do you let people know that you're there?
Drop your call sign.
Just throw out your call sign. If you throw out your call sign in the middle of a high frequency contact that somebody's making, if they can hear you, they'll say, yeah, breaking station, go ahead. Because obviously if you're breaking in, there's some compelling reason for you to do so. What control is typically adjusted for proper ALC? ALC again means automatic level control on a single sideband transceiver. So what? Yeah.
You said CQDX. How does anyone know where the calling station is from?
I hope they know your call sign, because you've given your call sign. So if I hear CQDX from N7EVK, I know I'm not answering.
And it's because like the first letters that you're here are gonna be the
Yeah,
country.
I know where he is. Because every country has its own prefixes. Okay, what control is typically adjusted for ALC setting? That would be the audio gain, transmit audio, or microphone gain. So if you're driving your ALC too hard, you back down your microphone gain. The other way to do it is actually, if you're using a microphone, you can pull the microphone away from your face. Which of the following is what is true of Vox operation versus push to talk? I don't like Vox. Why don't I like Vox? Vox means voice operated transmit. Why don't I like Vox?
Cuts off the first thing that you say.
Actually, it usually doesn't. That's not why I don't like Vox.
Might transmit when you don't want to.
That's
There you
exactly
go.
right. Because I'm sitting there and I'm sitting there and in my station and it's really cold and I spill a cup of hot coffee on my lap. Like, God damn it. Well, I just transmitted that over the air. So
But at least you didn't say one of those 7 words.
I've said, yeah. I might still say some of those too. So I was just trying to keep it a little bit clean. So it allows hands-free operation. I don't use it because it's hands-free operation. I like having to use my hands as a filter to filter what I get on the air. Okay, a practical way to avoid harmful interference on a clear frequency. Okay, you are sending QRL. We are now into operating courtesy and how to be a good world citizen on the air. So if a frequency sounds free, it maybe is not. The reason that it isn't is because now that we have done a little bit of propagation, we're going to draw a map of the world. And I'm station A, and there's station B, and there's station C. And station B and C are in the middle of a contact. Propagation is not uniform, as we have discussed. Station B and C are talking to each other, but at this particular time, station C is talking. I only have propagation with station B. Station C would basically be a black hole for me because of conditions, maximum usable frequency, etc. So if station C is busy chatting away, what do I hear?
Nothing.
Nothing.
Nothing. I hear nothing. As far as I'm concerned, the frequency is available. So, however, station B, if I ask that question, might have a different response, right? Station B, well, if I started calling on that same frequency, I would be interfering with station C. So the first thing I ask is on Morse code, I ask QRL question mark. That means, is the frequency in use? Is the frequency busy? The answer could be QRL, which means, yes, the frequency is busy. Please go somewhere else. On voice, I would say literally, this is N7JI, is the frequency in use? And if the frequency is in use, this station will say N7JI, the frequency is in use. Thank you for asking. So QRL means, are you busy or is this frequency in use in Morse code? Again, QRL. Which of the following complies with good amateur practice when choosing a frequency? Well, first of all, you need to make sure that you're allowed to be there, right? That's a very first thing. If your privileges don't allow you to transmit there, you have no point being there. Beyond that, you follow the voluntary band plan for the operating mode you plan on using. So let's take a look at our frequency spectrum chart right here and say that I want to operate on the 20 meter band I want to do voice, and I have a general class license. So I have a general class license. Notice it's the blue area here. What is my range of frequencies that I can use on the 20 meter band? I just highlighted in blue.
14.225 to 14.350.
Yep. Okay. So what if you hear a station that you really want to talk to down at 14.155?
Too bad.
That would be upgrade. Time to upgrade. That's one of the best reasons to get your extra class license, which is you have full access everywhere. You don't have to worry about it. So follow the voluntary band plan. So if I wanted to transmit on single sideband, if I look at, let's say 14.075, that would be down in this area. And why could I not transmit single sideband in that area?
That's the CW RIDI data mode.
CW RIDI data mode. Now, if it's a real emergency, the band plan is a voluntary band plan. It is not set in stone. The FCC has not said thou shalt not operate single sideband down here. But again, if you're operating outside the band plan, if it's an emergency, you better have a good reason for doing it. You might also get a nastygram from some volunteer monitors that say, hey, you were observed out of the band plan. Just so you know, you're outside of the band plan. Let's see, what is the voluntary band restriction for US stations on 50.1 to 50.125? That would be on the 6 meter band. Here's 50.1. And notice what it says up here at 50.110. Let me zoom in right there. Notice what that says. DX window.
Yep.
So 50.1 to 50.125 is the DX window, which means that if you're in the continental 48 states, you wouldn't make contacts above within that band. So you want to stay outside of the DX window unless you hear, let's say, Japan calling. If you hear Japan calling or even Hawaii calling, go ahead and answer. You could also go in that area and say CQDX, looking for stations outside of the lower 48. All right, when selecting a single sideband transmitting frequency, how far apart should you be from other stations? How many kilohertz?
At least the width of your transmitting signal.
Right,
So
and
3
typically
kilohertz.
3 kilohertz, that's right. And when doing a CW contest, for instance, Morse code has a bandwidth of about 150 hertz. You typically want to stay 150 to 500 hertz away from other stations. If you're in a contest, that is not possible, as you will find. It makes it incredibly challenging and sort of fun to try to work each other through the noise. So for CW, you want to stay 150 to 500 hertz away. If propagation changes during your contact and you notice interference from other stations, what should you do? You should try to solve it. Basically say, okay, well, we're going to move a little bit, or hey, you guys are starting to come in. Can you guys move? So you resolve the problem because nobody owns a frequency. Which of the following is true when concerning access to frequencies? Except during emergencies, no station has priority to any frequency. Now, the FCC can actually say during an emergency, 14.325 is our emergency frequency. Unless you have emergency traffic, stay off this frequency. That sometimes does happen. When is an amateur station allowed to use any means at its disposal to assist another station in distress? That would be at any time during an actual emergency. That would mean a bona fide emergency, earthquake, hurricane, life or death situation. My car's about to get washed over. My car's about to get washed over the falls. Do what you need to do. What frequency should be used to send a distress call? That would be any frequency that has the best chance of communicating the distress message. If somebody's going to hear it, if it's a real distress message, go ahead and send it anywhere. Again, you might have to explain what happened after, but that's okay. If it's a bona fide reason, you'll be okay. What should you do if you're communicating with another amateur station and hear a distress call break in? You drop what you're doing and acknowledge the station in distress and figure out how to help. And who can be the control operator of an amateur station transmitting in RACES? RACES is Radio Amateur Civil Emergency Service. So who can be the control operator of a RACES station during a disaster?
Someone with a license.
Yep, someone with a license, because RACES is Radio Amateur Civil Emergency Service. You get registered with RACES, you get registered with your civil defense organization, but if you don't have a license, you can't be the control operator of that station. Okay, we are on to Morse code, my favorite operating mode. What is the best speed to use when answering CQ in Morse code? If I hear somebody zipping along at 40 words a minute and I somehow manage to copy them, but I can really only comfortably copy 20 words a minute, how fast should I go?
As fast as you can comfortably go. Whoever's the
Right.
slowest.
Right, whoever's the slowest, that's how slow you go. So you want to send as fast as you are comfortable copying. You also don't answer faster than the CQ because let's say they're calling CQ at 15 words a minute. That probably means they can't copy faster. So you would go with the same speed. What is zero beat when talking about Morse code? If somebody is 0 beat, that means quite literally. So let's say here's a Morse code station on 14.006. That is the frequency that station is transmitting a signal. 0 beat means
Doesn't that mean they're copying it fast? They're copying as fast as it's being sent?
Well, let's say they're sending at 15 sending CQ at 15 words a minute. You wouldn't answer at 20. The assumption is that
But
they're
you're,
not going to
you're
be sending.
copying. Okay,
Yeah, basically you guys want to slow down to the minimum speed that everyone's comfortable with. Okay, 0 beat, that means that if someone's transmitting on 14.006, your transmitter would be transmitting also on 14.006. This comes from the fact that if we have a signal here and a signal here, and they're very, very close. We have any musicians here, David? What happens if you have two signals that are very, very close in frequency and you hear them at the same time?
Well, if one is slightly, well, even if they're really close, but if one is
Right.
slightly, because I play the mandolin, so I actually have two strings that are tuned close. And
Yep.
if one of the strings goes out of tune, it starts going wow, 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 wow.
That's known as a beat frequency. So that will actually cause a very, very slow frequency, which is the difference between the two. So 0 beat means that you are on exactly the same frequency. That's what it means to 0 beat the other station. Okay, when sending CW, what does a C mean when added to the RST report? Okay, RST.
Or unstable signal.
Yep, R is readability, S is signal, and 9 is tone. This is from 1 to 5, 1 to 9, 1 to 9. So if somebody is 599, that's a perfect signal. That's as good as you can get. Perfect readability, perfect signal strength, perfect tone. However, if somebody is, let's say, 596C, that would mean perfect readability, perfect signal strength, and you sound terrible. And it's because you have a chirp. Your signal sounds like that. Your signal is unstable and chirpy. Most often caused by running off of a battery on field day. And when you transmit, your battery voltage drops, which changes your transmit frequency slightly. And you'll actually hear a chirp like that. What does it mean if you send the Q signal, QRS? QRS means please send slower. Slow down, QRS. And you'll probably never send this for a while, but QRQ means please send quicker or faster. But we don't need to know that one for this. The next one, QSL. What does QSL mean?
I confirm.
I confirm. I got it. Roger. All good. All right. QRN.
Static.
Static. This is
Noise.
differentiated from QRM. QRM
Man-made
is
interference.
man-made noise. QRN is natural noise. So somebody talking over you would be QRM. Static would be QRN because it's naturally generated. Okay, QRV means I'm ready to receive. So if you're going to send me a message, QRV, go ahead. It means I'm ready to receive a message. Okay, next. If you are sending on Morse code and you say KN with a bar over it, which means it's all run together, that means that I'm specifically looking for the station that I called. This would be equivalent to me saying KJ7YZB N7JI, over. So
This is KJ7YZB. Go ahead and set
right. So now the question is, did I call anybody else?
Nope.
I specifically called that one station. That is what KN means. If I said, this is N7JI listing for a call from anywhere, anybody, anywhere, that would be the equivalent of me ending with the letter K. K means anyone, anywhere, come now. KN means just specifically the station that I've called, that I've identified. Okay, and finally, when ending a message, if you're sending a formal message, the message is, for instance, okay, this is This is for John Smith, 322 Main Street. John, I will see you at 4 o'clock, period. End of message. AR. The pro sign AR run together means end of formal message. So when the other station hears that AR, that means the message is over. All right, which of the following describes full break-in telegraphy, also known as QSK? Okay. So if I'm sending Morse code, it looks like this. Dot, dit, dit. So this is over a period of time. So da, 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 for instance. If I'm transmitting, normally what I would do is at this point, I would key my radio as time advances. I would key my radio at the beginning, send what I was doing, and then when I was done, I would unkey my radio. QSK means that every time I stop transmitting in the middle, like right here and here and here and here, my receiver actually momentarily switches back on. And during that time, I can actually hear stuff that's coming from outside, which is why it's also known as break-in. Because if somebody is trying to break in, I can hear them. So that's known as full break-in or QSK.
Is QSK a Q code or is that
It is.
like?
It's a Q code also. And colloquially, QSK is a mode of operating, which means feel free to break in, or I can hear you if you break in. Okay, volunteer monitoring program.
Oh,
HF
before you-
operations. Yeah, go ahead.
Before we go into that, why is it that you like Morse code so much?
That's a really good question. And I don't know the answer to it other than it's where I started. And I find it to be the most challenging, but I also happen to have gotten to the point where I'm really good at it. And I enjoy doing it. It's the most interactive way of talking on the air. Because it requires full brain involvement.
It seems like it would take a lot of concentration.
Yeah, it depends. I mean, I'm 52 and I've been doing it since I was 15. So, for me, Morse code is like it's another language.
Right.
And the fact that compared to other modes, it actually, because it has such a narrow bandwidth. I mean, here's a single sideband signal. David, what's the bandwidth on single sideband?
Just under 300 hertz or
It's
kilohertz.
3 kilohertz. Okay. Morse code is about this wide. About 150 hertz, which means that when you're using your receiver, you can actually filter it down so that you hear this, which also means that there can be somebody else right here using it as well, and someone else here and here and here and here and maybe in there, and there's another one here and there. So it allows for much greater reuse of the band because spectrum is a limited resource. So the more effectively you can use your resource, the better everything is. That and the fact that if I have let's say that I have two signals. I have my single sideband signal, which is 3000 hertz wide, and I have my Morse code signal, which is 150 hertz wide. And I have 5 watts of transmitter power to fill this. Essentially, each of these is like a bucket. So what will the depth of this bucket be if I have 5 watts? You actually measure that in watts per hertz. So that's the depth of the bucket. And in this case, it would be 5 watts per 3000 hertz, or 1/600th of a watt per hertz. Okay, so I take that same number and I divide 5 watts divided by 150 watts, 150 hertz. And I have 1/30th of a watt per hertz. Okay, so what do I see? How many times bigger is this than the other one?
200?
20 times.
20
20
times. Okay, 20 times. How many dB is that? 20 times is 10 times 2,
6,
So 13.
13
Six.
dB,
13.
right? Which basically means that to me, for my signal, it will be as though I will have a 13 dB bigger antenna system. That is a lot. I mean, that is a lot of gain, right? That's a big antenna just by switching from one mode to another, which is why when I'm operating QRP, which is my favorite operating mode, which is 5 watts or less, Morse code works a heck of a lot better than single sideband does, because I have an inherent 13 dB advantage. And how many S units would that be? One S unit is how many dB? 6 dB. So essentially my signal, if we were comparing it, would be 2 S units better on your receiver. So on voice, I would be an S3. On code, I'd be an S5. Maybe I pop out of the noise a little better. And on top of that, the other station has the ability to turn on their filters and be able to pick me out even better out of the noise. So there are a lot of distinct advantages to operating a very, very narrow bandwidth signal.
Hey, Scott.
Yep.
So from a mobile maritime, like on a boat, emergency communications standpoint, would continuous wave be like, it's a huge hands down the best emergency communication mode?
Well, it totally depends. I mean, PSK31 is another one of those that's digital and really, really narrow bandwidth.
Oh, okay.
And if you're just trying to get a hold of somebody, it's kind of hard to send a message, but you can use FT8. FT8 is exceedingly low power levels and extremely efficient. A lot of forward error correction.
Okay.
So yeah, voice is actually probably the least efficient way to get someone's attention, unless they're like super strong. All right, volunteer monitoring program, page 77. Volunteer monitoring program is amateur volunteers who are formally enlisted to monitor the airwaves for rule violations. These are not FCC employees. These are people who have registered and gone through the program with the American Radio Relay League, or ARRL, which is the National Association for Ham Radio in the United States. And basically, you don't want that to get to the point of the FCC knowing about it, which is why we have this volunteer monitoring program. If it gets to the point that the FCC is knocking on your door, then you have trouble. So we want to stop it before it gets to that point. What are the objectives of the volunteer monitoring program? To encourage amateur radio operators to self-regulate and comply with the rules. In other words, we're going to point something out. Now it's your job to go figure it out so that the FCC doesn't have to be involved. What skills learned during hidden transmitter hunts are of help to the volunteer monitoring program? That would be direction finding. You know there's some interference coming from somewhere. Somebody's transmitter's a little dirty. You can do direction finding and be able to find out where that illegal signal's coming from before the FCC finds it. What is an azimuthal projection map? Okay, I believe this is one of those things that I actually sent out as well. And I did, look at that, azimuthal map. Okay, I'm gonna show this on the screen because I'm just showing a big white screen right now. Okay, so this is an azimuthal map. So an azimuthal map shows true bearings and distances from a particular location. If you're not in Oregon, I'm sorry, you have to make your own map. If you go to NS6T's website, you can actually generate your own based on where you are for free. That's how I did this one. So this basically says that the Earth is 24,000 miles around. So from here to halfway would be 12,000 miles. So if I go east to the 90 degrees, notice I encounter no land. When I go over to 90, that wraps me all the way around to 270. When I come back to 270, back along 270, I finally get to Australia. So if I continue on, you notice that I go all the way back to where I started. If I head west, the first thing I get to is New Guinea, and then Australia, in particular, like Perth. So that shows you that there are really two ways to get to any point on the Earth. So this shows you heading and distance. So there are two paths, for instance, to get to Australia. There's the short path. And if that's all the way to the outer edge of the ring is 12,000 miles, then each of the small rings is 3,000 miles. So from here to Western Australia, it's about 9,000 miles. I could also go the other way heading east. It would get 12,000 miles to the end of the map. And then you come all the way around and it's another 3,000 to get back to Australia. So that's an azimuthal projection, true bearings and distances. So how's a directional antenna pointed when making a long path contact? Well, Australia is due west of here. So if I want to go long path, I would point due east. Now it's 15,000 miles instead of 9,000 miles. Which one is more likely to work?
The short one.
It depends.
It
What
depends.
if I'm on the 15-meter band and it is nighttime between here and Australia directly? So that whole path to the east is all lit up because it's winter, so it's southern summer, which means the South Pole is still in sunlight, and the ocean path heading east is in sunlight, and then it just has to basically get from Antarctica up to Australia. On that particular band, it's entirely possible that the long path is actually the better path.
Okay.
It would be fascinating to see a daylight projection overlaid over this azimuthal projection.
And actually, I have that. Oh, I don't have it with me. I'll try to find it. I'll find it at the next break. Okay. So that's long path. All right. Which of the following is typical of the lower HF frequencies during the summer? All right. What is a characteristic of summertime? What happens on hot days?
Long daylight too.
Long daylight, and what else? What happens?
Lots of
if you-
ionization. all the way
Lots of
to the
ionization. And what
light.
happens if you live in Florida every day at 3 o'clock in the afternoon?
Thunderstorms.
Thunderstorms. Thunderstorms make lots of lightning. Lots of lightning makes lots of
Interference?
static crashes. Exactly. So on the lower frequency bands, so 80 meters in particular is just hammered during the summertime because of all the thunderstorms and the fact that at night, what is the layer of the atmosphere that dissipates? The layer of the ionosphere that dissipates at night?
D.
The D layer goes away, which allows those low frequencies to propagate. And all those static crashes from all the way over in Florida and the Gulf states and everywhere else, they just emanate everywhere. And if you listen to 80 meters in the summer, you'll hear this. It's a constant barrage of static crashes. It's really fascinating. Okay, which of the following is a good way to indicate on a clear frequency in the phone bands that you're looking for a contact with any station? CQ, CQ. This is N7 Juliet India, N7JI calling CQ and listening. So call CQ and give your call sign. All right. So does everybody know, because you're all hams, does everyone know the phonetic alphabet?
Yep.
Yes? Okay.
Yep.
and it's the standard phonetic alphabet: Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, et cetera, et cetera. All right, that is likely to be on the exam too. Which of the following is required when participating in a contest on the HF bands? The only thing that's required is you still have to identify your station as you normally do. How often do you identify your station?
One,
Every 10 minutes
Every 10 minutes and
after the end of the
at
contact.
the end. That's right. So this is one of those places where during contests, the rules are like, well, you know, what's considered at the end? This is a perpetual thing. So for instance, let's say I'm answering Matt, go ahead and call CQ contest.
KJ7CNL CQ contest.
November 7, Juliet, India. I just replied.
Okay.
I didn't even call you. I don't have to.
I've never done any contesting actually. So
And then you just give me my call. You just repeat my call sign to indicate you got it and give me a signal report.
Okay. And N7JI, this is KJ7CNL. QSL.
You didn't give me a signal report.
Oh,
All
okay.
I want is my call sign and a signal report.
Okay. N7JI 577.
Okay. KJ7CNL. Thank you. 59.
KJ7CNL.
And then you say contest again. Notice what I didn't do after that. I didn't give my call sign at the end. So there's a little bit of ambiguity as to the rules constituting how long you plan to be on and what constitutes the end. Realistically, I should say N7JI as soon as I'm done, but the whole thing only took about 5 seconds. So like, here's the exchange that like I would give. It's like, CQ, this is N7JI contest. And the reply would be N7TB, N7TB 59, N7JI 59. Thank you. Next, QRZ. So, I mean, it's rapid fire so fast, and maybe we'll get to listen to a little bit of that on WebSDR too. You still have to identify your station per normal operations. Okay, QRP operation. I knew this might come up. QRP is low power. That's what I enjoy operating. By convention, it means 5 watts or less. So QRP is low power operation. Why is it important to keep an amateur station log? And that is to help with a reply if the FCC requests information. It used to be that you were required to keep a log. That is no longer true. The FCC would actually say that everyone had to give a log and keep a log. And not only did you have to keep a log, you had to keep a log of every time you keyed your radio at all, which meant I wrote down in my log that I tuned my antenna. That would actually be a loggable event. That used to be the case. That was a pain. The FCC did away with that, thankfully. Okay, here we go. Digital operating procedures. All right, what segment of the 20-meter band? We're going to put this up on the screen. I got to pick the different one. Okay, here we go. What section of the 20-meter band is set up for digital transmissions? Typically on this band, notice where it says PSK 31 14070. That actually should say 2150. Realistically, it's 14070 to 14.112. Those are typically for propagation beacons. Excuse me, for digital communications. 14.100 is the 20-meter propagation beacon band. So that basically means that those propagation beacons are always running, and if you're operating on the digital modes, you try to stay away from those. In what segment of the 20-meter band is PSK 31 most commonly found? No, I shouldn't have unshared that because that's what the next question was. Here we go. Okay, notice PSK 31 says 14.070. There it is. 14070 is the PSK 31 band on the 20 meter band. Next, what segment of the 80 meter band is most commonly used for digital communications? Notice this says auto digital down here. 3.585 to 3.6. So this is where you typically find digital communications on the 80 meter band. And in reality, it's a little bit more space than that. It drops down to about 3.570, 3.573 is the FT8 frequency. But you can't go above 3.6 on digital, because once you do that, you're into the voice band, which I think is actually a little excessive. There's been talk about reallocating those bands a little bit because they're skewed so much toward the voice band. So here's a question. On what of these bands can you operate Morse code?
All of them.
All of them and everywhere. You can do Morse code anywhere on any band.
Is that another reason you like it so much, Scott?
It is. It is. Okay, what is the most common frequency shift for radio teletype? In the amateur bands, the most common one is 170 hertz. They're known as mark and space, and the frequencies are nominally 2,125 hertz and 2,295 hertz. And if you have a receiver that can do RTTY using FL-Digi, which is the software that you use, it's actually very pleasant to listen to because you can tune around anywhere on that band and tune them in. If you have a receiver that actually listens using RTTY, like a RTTY setting with a crystal filter, it sounds uncomfortably high pitched because those frequencies are 2,125 and 2,295 hertz. The spacing is 170 hertz. That's always true. On at least on 170 hertz shift RTTY. Which mode is normally used when sending RTTY signals using AFSK on a single sideband transmitter? You know, it's interesting that the answer here is lower sideband because this has been the case over a long period of time. But with the advent of all the software that people use, FL-Digi in particular, to send teletype, a lot of people do use upper sideband RTTY. So, but I guess by convention, normally you would use lower sideband. What's the standard sideband used to generate JT9, JT65, or FT8 digital signal? That's basically the everything else. That's upper sideband everywhere. Which of the following connectors would be a good choice for a serial data port? They list it as a DE9. I always thought it was a DB9 myself.
I always thought it was a DB9 too.
Yeah, but I'm thinking that the DE9 must either be a typo or
No, DE9 was apparently the correct way all along, and we
yeah.
just
Well, I mean, it could have been a typo in the FCC data in the question pool, and they never fixed it. So, but anyway, think D something 9. That's your standard data port for serial connections. A characteristic of the FT8 mode, FT8, you send nothing but, go. So here's what FT8 looks like. It's 15 seconds per person. So station A sends CQ N7JI CN84. Okay, CN84, what is CN84?
grid coordinates.
square.
That is a grid square locator. So if we look at our chart, we will see that one of the things that I sent you guys was a grid square locator chart. And let me share that. Okay, so here is a grid square locator chart of the United States as it fits into the rest of the world. The entire world is separated into grid squares, which are actually grid rectangles. They're 2 degrees wide in longitude by 1 degree in latitude high. And of course, they're actually not quite rectangles because they're on a curved surface as well.
Hey, Scott, you said you sent this out. Did you put it on the reflector? I didn't see it.
Oh, I can forward it to you then.
I don't remember seeing it.
This was in the packet on the email, but I don't know that all the emails had the packet attached to it.
Yeah, let me send it. Ken Wyman packet. Okay, we just attach it, and here it comes, Ken.
Thank you. Yeah, I didn't see it come in.
It's almost done. Whoop. Okay. Okay. So anyway, the whole world is split into grid squares. And notice in Oregon here, we are in CN84. And John, where are you exactly on this?
BO 40 or 31. 2 million.
BO 31. So you're
No, no, I'm
down
sorry, BP. I'm BP 31.
BP 31. So near Anchorage.
In
Or-
Anchorage, yep.
Yeah. And let's see who else is somewhere else. Lisa, what's your grid? Where are you?
Oh, in Colorado,
Where in Colorado?
Fort Collins.
Okay, so you're probably like DN70.
Yep.
It's up. So there you go. So everybody, it's good to know your own grid square. And if you operate on FT8, you definitely didn't need to know that. And the
So on
reason that
in the contest this weekend, I heard someone from Hawaii, and I wasn't quite sure how to respond back.
well, that was not using grid squares. That's using CQ zones.
I didn't know. I was confused. Yeah.
Yeah, you just got to go find the rules. So your CQ zone map. Yeah, I'll put this up too.
So CQ zone map's different than the grid square map.
Oh yeah, here's CQ zones.
Yeah, I looked that up on the internet and it's like, huh?
Yeah,
So we're zone 3.
we're zone 3. So you just give 5, 9, and 3. Hawaii would be zone 31. Worked a bunch of China. China's zone 24, zone 25. Here's Australia, zone 30 and 29.
Yeah, well, so I wasn't getting 5 9s. It was really difficult to to get a good signal.
Yeah,
So,
but it doesn't matter. Everybody's 5, 9. Nobody
Really?
wants to hear you give a 5, 6 during a
Really?
contest. Oh,
Is that
of course
right?
not. Yeah. It could be, nobody wants to hear that. Everyone's 5, 9. Because if you're not, because if you don't put 5, 9 in your log, then they actually have to write what the real report was. What's important is that they heard you. If they heard you, then you're 5, 9.
Really?
Yeah, really. Everybody's 5, 9.
That's what I was hearing, but I tried to call back to Hawaii and they didn't hear me. So
Yeah, they were pretty busy yesterday, actually. Okay, so CQ, N7JI, CN84. Okay, the reply to that would be N7JI, N7EVK minus 12. That would be a signal report in decibels compared to the local noise floor. The reply to that would be N7EVK, N7JI, R minus 16. That would be received and you're a minus 16. The reply would be N7JI, N7EVK, RR73, which means I've got it and goodbye. And my reply to that would be N7EVK, N7JI, 73. That's it. That's an entire exchange in FT8 or any of those digital modes. Essentially, you're exchanging, well, and part of this also right here could be CN84, also the grid square. So it could be a little bit longer depending on what you're doing.
But
Essentially,
that's
what's exchanged
automatic, right?
And they're generated automatically by your software. So what's exchanged are grid squares, signal reports, and call signs. And that's it. Call sign, grid square, signal report. Basically, make contact, get it in the log, and move on. If you want to make
You're
contact,
talking about, this is like contesting or something?
no, this is FT8. That's actually what's in the following is a requirement when using FT8. We're on page 80 of the book. So that's what you do when you're operating in FT8 or any of the JT modes. So this is actually a mode that's designed for really weak signal work, such as terrestrial, really long distance stuff, or very low power, or also EME, which is Earth, Moon, Earth, and meteor scatter, where you basically just want to establish that you were able to make contact and that's all you need. It's not a rag chewing mode where you would like have a conversation or anything. So you exchange grid squares and signal reports and call signs. And that's all you need.
In an emergency, would it be appropriate to somewhere in there then say, hey, you know, SOS, my boat is sinking or whatever?
You can, well, you're limited to 17 characters at a time, and it takes 15 seconds to send them. You can write a free form message, but it's more difficult to send and it's more difficult to receive. So PSK31 would be a definitely, if you can find somebody to talk to on PSK31, it's a better mode to use because it's keyboard based. So if you're using a keyboard anyway, that would be, you know, basically you can type messages. And here's another one. If you are doing that, would you use upper or lowercase? Everybody?
Lowercase.
Lowercase is faster than uppercase. Right. So for PSK, 31 uses varicode again. Lowercase is greater than upper. Higher data rate using lowercase. All right. So if you're also operating on FT8, it's important to remember that your time synchronization has to be plus or minus 1 second. Everybody who's operating has to have a somewhat accurate clock to be synchronized with the 15-second periods. If you can't decode a RTTY or other FSK signal, even though it's tuned properly, you could have mark and space reverse. You might be on the wrong baud rate, and you could also be on the wrong sideband. Basically, the baud rate is how fast your mark and space are coming. Wrong sideband means they'll be flipped, and mark and space means they'll be flipped, in which case you're not able to decode a letter P as a letter P, for instance. Let's see, which communication system uses the internet to transfer messages? Matt.
WinLink.
WinLink. Matt, give a 3-minute discussion on WinLink, if you would.
Oh my
Go.
God, really?
Yes, really. You have 3 minutes.
Okay, with WinLink, you type up a message, and the message can include attachments, preferably less than 20 kilobytes, because it takes so long to get the message across. You can use a variety of methods to send the message over the air. There's venerable Cantronics KPC3. There's the SignalLink USB. That's hardware and software difference between the two. Okay, once you establish a message and you type it up, just like any other email, you don't send it right away. You post it to your outbox. Yes. Then you connect to any other WinLink remote message server, or RMS, whatever it is, a remote message server, remote mail station. Can't remember the acronym, but anyway.
That's going to be another ham station typically?
Yes. You can send it directly to another person, or you can send it through a WinLink server. That's the difference between peer-to-peer and WinLink message. And you can, once at a WinLink server, it can go over the internet to any other internet user with an email address. And let me see. And yeah, it goes to the general internet from there.
Okay, how about working the opposite direction? Can an
What?
internet user send an email to a WinLink user?
Yes. I sent it to your call sign at winlink.org. And then when you connect to a remote message server, the message will be waiting there for you.
Okay,
I think that's it.
cool. All right, so who can use WinLink?
Any amateur radio operator.
Okay, so is it actually a private system in any way, shape, or form?
Don't think so, no.
Okay. Cool. All right. Which of the following is a way to establish contact with a digital messaging system gateway
Well,
station?
hold on, let me elaborate on that. It is
Yep.
absolutely not a private system in any way. Anything you send out there can be viewed by a third party. So because it's amateur radio, no expectation of privacy, right? So anything you send out there can be viewed by anyone at the RMS or anyone listening, really. So there's
And
no
your-
real expectation of privacy.
And your messages also have to meet the same decency requirements that our operations over the air do.
That's correct. I think we covered it.
Okay, cool. All right. So that is WinLink. That's a system used to use the internet to transfer messages over the radio. Which of the following is a way to establish contact with a digital message system gateway station? Transmit a connect message on the station's published frequency. I was using packet BBSs long ago to do exactly that back in the 1980s. Very, very slow packet radio.
I got a quick question.
Yep.
Earlier, I looked up what the differences were between general and technician. And in this hamradioprep.com, it said WinLink is an HF-based email system that can be used nearly anywhere. WinLink is just another good reason to get your general license if you're
I would
interested.
agree with that.
And
Yeah.
so it's only, you have to be a general license holder.
No,
to use it?
Uh,
but you have
I'm
to be a
still tech.
general license holder to access a lot of those frequencies.
Oh, okay.
I mean, I think you could probably do WinLink over 10 meters.
If you find a 10
If you found a gateway.
RMS, yes.
Yeah.
Okay, so you can use WinLink either way. It's just you don't have as wide a variety of bands to use.
Correct.
Okay.
All right. How can a Pactor modem or controller be used to determine if a channel is being used by other stations? You put the modem or controller in a mode which allows monitoring communications without a connection. And as Matt was saying, if you're on the air, you can't encrypt anything. The only times we're allowed to encrypt are if you're sending information to a remote controlled craft or sending information to a space station, like you're controlling a satellite. Those are the only times we're allowed to encrypt anything to hide something's meaning. So if you're going to be sending a message over WinLink or WinMore or Pactor or anything like that, you better not say anything too personal, because anybody can see it. What systems which symptoms may result from other signals interfering with a Pactor or WinMore transmission? Might get frequent retries, timeouts, long pauses. Basically, it's a digital communication system. And if you have signals interfering, that's lots of errors. If you have errors, you're basically going to have a higher error rate. So frequent retries, timeouts, long pauses, takes a long time, or failure to establish communications. And how do you join contact between two stations using Pactor? The answer is you don't. Pactor is one station to one other station. So basically they have a direct link between the two. Okay. Electrical and RF safety. All right. What is one way that RF energy can affect human body tissue?
Heating.
Think of a microwave oven.
Heating.
It's not causing genetic damage, but it certainly is warming you up. What is time averaging with regard to RF radiation exposure? That means that you look at something over a long period of time and see what the average is over the period of time. So if you're transmitting at 100 watts for 6 minutes, and your averaging period is 60 minutes, then your average time, your average transmitter power is 10 watts because it's 100 watts for 10% of the time. The rest of the time it's 0. So it's time averaging. So why does transmitter duty cycle? What does it have to do with evaluating RF exposure? Basically, if you're looking at average exposure, you can transmit for a short period of time with higher power levels and turn it off for a long period of time, and that lowers your average, reducing the overall exposure. When evaluating whether a signal exceeds the maximum permissible exposure, what do you look at? Duty cycle, frequency, and power density. What should you do if you're installing an indoor antenna? So what I'm going to do is pull up this website here, which I think everybody should at least look at some point. And it's called hint link power density. And I'm going to put this out into the chat because this is really, really helpful. All right, and what this does is it's an RF exposure calculator. This determines whether or not, per FCC regulations, your station is safe for you or for just the general public who happen to be walking by. So let's say you're transmitting at the antenna, you have a 50 watts actually getting out. Notice that this says dBi. Does everyone remember what dBi stands for?
Decibels with regard to an isometric antenna.
Close, isotropic. But
Yeah.
yeah. So notice it says enter 2.2 for dipoles, because a dipole compared to dBi is 2.2 dB better. So we're going to go with just a plain old dipole, 2.2. We're going to be 10 meters away from it, and we're transmitting on 14 megahertz. Include ground reflection effects, which basically means assume a perfect ground and go. So what this means is that this says, okay, at this particular frequency, with this particular power level, with this antenna, if you're 10 meters from the center of the antenna, you are allowed this power density. Right here for a controlled environment, 4.6 milliwatts per square centimeter. And that's basically a flux. How much wattage per square centimeter? An uncontrolled environment means that basically that means that anybody can walk into the room or walk by the antenna. You can't control them. You don't have a fence put up. So here's the actual calculated level, and here's the maximum the maximum that's permitted. This also says that, okay, with those numbers, somebody could get to within 4.5 feet of it and still be safe. Well, if you're putting an antenna inside, you might actually get there pretty quickly. So that means that, you better actually do you better do a calculation based on being indoors. And it also means don't touch the thing. So make sure that MPE limits are not exceeded in occupied areas. MPE is maximum permissible exposure. All right, which of the following steps must an amateur operator take to ensure
Hey, Scott.
compliance? Yes.
So if you have the antenna on your roof mounted to your chimney,
I wouldn't worry too much about it, but go ahead.
so if you're 20 feet away or 10 feet away from that and you're putting 100 watts into it, what would that look like in your house?
Let's take a look. Okay, so let's say 100 watts, but that's average power. That means you're operating full power all the time. Are you operating full key down power all the time?
Of course not.
Right. With a feed line that has no loss. So let's take absolute worst case, which is you have a perfect feed line with no loss and a full key down transmitter. You're transmitting 100% of the time. All right. Let's say you have a dipole antenna. Distance is, you said 20 feet. So we're going to go with 6 meters on the 20 meter band. And there you go. You could actually go and do these calculations yourself without this website, but this website is really, really helpful. And
So a
actually,
so a controlled environment means what?
that means inside your house where you can control who goes where. People are aware of the existence of the hazard.
So that
Uncontrolled
doesn't look-
environment means outside your house where anywhere the general public could walk by and they have no idea what's going on.
So based on that, 2.87 feet?
Yeah.
What's,
You could actually
So-
get to within 2.87 feet of your antenna and still be okay. That's what it means.
but what you said earlier, 100% duty cycle at 100 watts. So there's
Right.
no,
That's right.
there's no duty cycle shown in this exposure calculator.
It's right here. That is where it says the average power at the antenna. Duty cycle works into that. If you have a 100-watt transmitter and you're doing 50% key down, right? You're transmitting half the time and receiving half the time, then you're at 50 watts average. And you just run the calculations again. Notice average power at the antenna. Then, okay, you've gone through and said, I lose 10 watts of transmitter power in my cable. Okay, so we're at 40 watts. There's my new calculation. There you go. And you just run it, print out a copy of it, and put it on the wall.
So worst case would be 100% all the time.
Right, which is why I went with absolute worst case. So if you're fine with absolute worst case, then you're definitely fine with anything less.
Interesting.
Actually, and that's a requirement. The FCC requires us to do that.
How does frequency change those distances? So like when you're in higher frequency bands versus lower frequency bands.
So if you're on a higher frequency, for instance, let's go with 40 watts, but now actually let's take it and put it on 144 megahertz. Put us on the 2 meter band. And notice the uncontrolled environment is 0.21 limit. Now we'll maybe take it down to 10 meters, and the uncontrolled environment is 0.92. So the higher the frequency, typically at up to a certain point, the lower the permissible limit. So if I went with 432, for instance, now it went up a little bit. So, and that's based on how, that's based on our resonance at certain frequencies and wavelengths. Now,
But what-
there is something
about-
else.
What
There's
about 2
something-
meter hand talkies and stuff like that that are
Good
transmitting,
question.
say, 7 watts?
Yeah, okay, so let's go with 7 watts. And we have a antenna gain of, let's say, 1 dB, because it's a crappy antenna, but you're half a meter away from it. And look at that. Controlled environment, estimated density, 0.71. You're allowed 1 milliwatt. Now, if it's you, you're okay. If it's not you, you're not okay. So what that really means is that your HT is potentially the most dangerous thing you have around. And that's at a distance of 18 inches. We can knock it down to a foot. And there you go. At a foot, at 7 watts, this is an unsafe environment if your average power is 7 watts. If you're only transmitting for, 10%, or let's say 10% of the time, then it's 0.7, and now it's safe. So it comes down to average power. Now, you can also do something else like this, where you say your average power at the antenna is 400 milliwatts, and you have a 30 decibel gain antenna. This is a dish, right? This is basically a microwave dish. And you're 10 meters from the antenna, and you're operating at, let's say, 2400 megahertz. Well, guess what? You're still okay. But now let's get closer to our microwave dish, and we're going to be 1 meter away. Guess what? How much, what's our actual transmitter power? 0.4 of a watt, but we have a 30 dB dish, right? This is essentially, this is a ubiquity and this is a ubiquity router antenna, a dish antenna. That is not safe to be about 1 meter away from it in front of it.
Yeah, 2.4 gigahertz. Try the 5.8 gigahertz just for
Okay.
fun. That's a more common.
Still not safe.
Still not safe. Okay.
Nope. That's at 400 milliwatts, because 400 milliwatts with a 30 dB antenna is the equivalent of 400 watts in the forward direction. Very, very important to do this. Okay, so how do you actually figure out whether or not your system is in compliance? FCC OET Bulletin 65, that website that I just showed you, which I recommend that everybody looks at, actually implements FCC OET Bulletin 65. You can also do your own computer modeling or do your own field strength calculations. How can you measure your RF field strength? You use a field strength meter with a calibrated antenna. So as opposed to relative numbers, basically you would have a calibrated field strength meter and a calibrated antenna. So if your system shows RF energy radiated from your station above permissible limits, you can take action to prevent exposure to the excessive fields. That means putting up a fence. Part of that action could be that you limit your time of operating. You know, you only transmit 10% duty cycle instead of 30. One thing that can be done if the evaluation shows that a neighbor might receive more than the allowable limit. If it's a directional antenna, maybe you don't point the antenna toward their house. If you don't point their antenna toward their house, the gain goes down. If you adjust or repair an antenna, turn off the transmitter and disconnect the feed line. That was always one of my biggest concerns when working on the tower when I was in college, that somebody would be down in the shack, not know that I was up on the tower, and key up the radio. So put a note on it. Even better, disconnect the power cord and put a note on it, and then disconnect the cable. So somebody would really have to be stupid to do this to you. Even better, lock the door and make sure that you have the key. When installing a ground-mounted antenna, make sure that it's installed in a way that it's protected against unauthorized access. So keep the dog away from it. Keep your kids away from it. When climbing a tower or using a safety belt, confirm that the belt is rated for the weight of the climber and it's within its allowable serviceable life. If it ever is activated, let's say you're on a tower and it falls and the thing goes boing and keeps you from falling, it's time to get a new belt after that. It's not designed to be used multiple times after it saved your life once. When you're going to climb a tower that supports electrically powered devices, make sure that all circuits supplying power to the tower are locked out and tagged out. That's basically exactly what I was saying with the other people in my club. Unplug it, put a note on it. Official lockout tagout means that I would actually put a lock on the power supply. That would be lockout tagout. I do this at work all the time. Why should solder joints not be used with the wires that connect the base of a tower to a system of ground rods? And that's because lightning generates enough energy that it will melt the solder and then you won't have anything anymore. What we usually use is actually just a bolt to hold it in place, or we will use something called copper weld. CAD weld. CAD weld is basically an incredibly high temperature magnesium fire, which proceeds to melt the steel and put a new steel, filler in between the two pieces of metal. When doing lightning protection grounds, they have to be bonded together with all other grounds to each other and to everything else. National Electrical Code, what is covered by that? That is electrical safety. What's the minimum wire that can be used with a 20 amp circuit breaker? Anyone know that? What
14.
gauge? Number 12. 14 is good for 15 amps. Number 12 is good for 20 amps.
Where did you get that information?
That is in the NEC. And that's
NEC.
actually National Electrical Code.
Okay.
And that's we're on page 85.
Can we get like a table with all that information in it? I've been looking for that.
Oh, there's so many tables in the NEC, it'll make your head spin.
Okay,
that's
where do I
why-
find the
that's-
particular one?
Yeah, well, that's why you just know that, if you need to distill it, there's a couple of things. 14 gauge is good for 15 amps. 12 gauge is good for 20 amps. 10 is good for 30.
Okay,
So that's it. What you need to know for this, number 12 is good for 20 amps. Number 14 is good for 15. Which wires in a 4-conductor connection should be attached to fuses or circuit breakers? A 4-conductor cable. All right. So normally we don't think about 4 conductors. The only place in your house that you'll find it are on your oven and you're on your dryer, typically, and maybe on your hot water heater. Typically, we have a line, a neutral, and a ground. Those are our 3 wires. This is at 120 VAC, which is not really accurate to say plus. This is known as hot. This is neutral. And this is ground. In the United States, what color is our neutral wire?
white,
It is white. That's right. What color is our hot?
black,
That is black. And how about the ground?
green.
Green. It could also be green with a little yellow tracer. So this is white. All right. So sometimes in your house, you will actually have a second one, a second hot. So that what you'll have is 2 hots and a neutral and a ground. The way this is set up is that you have line 1 and line 2 and then a neutral. And the neutral is also grounded. So that you have 120 volts here and 120 volts here. Very often what will happen is you will have an amplifier, if you want to buy an amplifier, that requires 240 volts, in which case you have 1, 2, 3, and 4 wires going to it. You have 2 hots and a neutral. Both hots will get a fuse. So you'll have a fuse on both of the hot wires. Okay. Which of the following conditions will cause a ground fault circuit interrupter to disconnect 120 or 240 volt AC line power? Okay, what does a ground fault breaker do?
Text if a human touches a load line or a hot line.
Actually, it doesn't. Well, it does. But
Yeah, actually, it's an imbalance between the return and the neutral.
That's right. So what happens is it has a sensor in it that looks at the current going this way and the current going this way on the line and the neutral. Because if this is a load, let's say this is a hair dryer. Ideally, this is a heater and the power goes in through the hot and back out through the neutral and back to where it started. These had better be the same. The reason they'd better be the same is because if we have some current that goes this way, we call that a ground fault. What happens is, does it ever show up coming back? It does not. It went a different way. So you have this current going this way and a different current going back that way. And if this varies by more than about 5 milliamps, that means that it's going somewhere else. It could just be something as innocuous as, a little bit of like breakdown in insulation here going to ground. It could be that somebody actually touched this and is the path to ground, in which case this will trip and save the person's life. So that is the purpose of having a ground fault breaker. So if you have a fault between one of the hot legs and ground, that will trip the ground fault breaker. Purpose of a power supply interlock. Every so often, somebody is killed by one of these because they disconnected it. So let's say that this is an amplifier, and you decide to open the lid and see what is in the amplifier. And there's a switch right here. So you open the lid. That's a terribly drawn lid. But let's say you opened the lid on this amplifier so you could see inside it, and you really wanted to do a test on it. So you opened the lid and you put a pry bar in there to keep it from slamming shut. And then you take your finger and you push down on this interlock switch. What is that interlock switch designed for? It is designed to turn off the unit when the door is open. And because this amplifier might have 3000 volts floating around inside it. And then normally with the switch, with the door open, you stick your finger in and you don't get electrocuted. But if you do something to defeat this interlock switch, you're now exposed to 3000 volts inside, which will kill you very, very quickly. What do you do when powering your house from an emergency generator? We covered this yesterday. What would you do?
Disconnect from the transmission line so you don't feed back something.
Yep,
Yeah.
disconnect the incoming utility power feed so you don't kill a worker who's working on the power lines. Which of the following is true of an emergency generator installation? It should only be used in a well-ventilated area because of
Carbon monoxide. and
carbon
having
monoxide
access.
poisoning. That's right. So put it outside. Put it outside somewhere far away from an air intake into your house. Because if you have an air intake, it'll pull the carbon monoxide into your house and suffocate you. Which of the following is a danger from lead tin solder?
Lead contamination.
Yep, lead contamination. Lead causes neurological damage. And okay, so we are on to the last 10 pages of this. And how about 20 minutes for lunch? Does that sound like enough? Everybody's home, right?
I'm not, I gotta run to grab lunch, so.
Okay. Well,
But if I miss the next 10 minutes, that'd be okay, I suppose.
okay. Well, let me look and see what it is.
Yeah, it's gonna take me longer to get home and set up again, Scott.
Okay. Let's see. Yeah, okay. How about 12:45?
That'd be perfect.
Okay, 12:45 it is.
Okay, bye.
All of those tall models that I have to take every fucking one out of the cupboard every time I want to get something that's behind something. I wanted to put them in a container, a basket, a box, something, so that I could move them as a unit and not have to unload it every time I want to get to something. That is clearly not going to happen today, so don't touch anything. Want food or something, just work around it.
All right, is anybody having lunch with me here?
Recording in progress.
That's Kilo Fox 5 Whiskey Charlie Papa. Charge that. Kilo Tango 4 X-ray Hotel. Something Foxtrot 5931 Foxtrot. Kilo 1 Quebec 3 Foxtrot 595. Kilo Quebec 3 Fox. Charge that. Kilo Tango 4 Echo 1. Kilo 6 Echo Lima Echo 5931. Thank you. Kilo Tango 4 X-ray Alpha. Kilo 3 Fox, Kilo 0 Fox Uniform Zulu 5931. Whiskey Hotel 7 Tango. Kilo Tango 4 X-ray Alpha. Whiskey 4 Ocean X-ray 5931. 595. Thank you. Kilo Tango 4 X-ray Alpha. Hotel. Kilo Charlie 2 Tango November 5931. 595. Thank you. Kilo Tango 4 X-ray Alpha. Whiskey 1 Bravo Radio United 5931. Thank you. Kilo Tango 4 X-ray Alpha. Kilo Tango 4 X-ray Alpha. There's something 1 Victoria 5931.
November Radio 5, November, you are 5904. Thanks, November Radio for Lima. Victor Alpha 7, Charlie Tango Golf, you are 5904. Kilo 9 Queen Alpha 5912. 04 QRZ. Kilo 10. Kilo Romeo Unit Whiskey 5912. Thank you. X-ray equipment 1 Kilo Zulu. Kilo Radio 4 Foxtrot. Kilo Radio 4 Foxtrot 5912. Hello, Mexico 5813. Okay, thank you, my friend. Again? Okay. QSO, you have it correct. Okay.
QSL 59. QSL. Yes, sir. Charlie Radio 2 Mike.
Canada, Quebec, Earth, Mexico.
Hey, Canada, Quebec, Mexico. Voilà, 59-14.
59-14, multiplicador aqui, ok, Mixab, honesto, 3, eu vou contar.
Ok, obrigadinho, meu brother, prazer em ouvir. 59-14. Por si também, eu de boa sorte para vocês, ok?
Sorte, um abraço, Heraldo.
Ok, tá bom. USA, Charlie Radio 2 Mexico. Whiskey. Charlie Radio 2 Mike. Again. Charlie Radio 2 Mike. Whiskey 8 X-ray Zulu 5914. You're 59, you're 59. 05, thank you, good luck.
November 4, Oscar X-ray.
November 4 Oscar X-ray 5914.
595.
5, thank you, good luck. Charlie Radio 2 Mike. Charlie Radio 2 Mike, contact.
Whiskey Zulu 5, Mike.
Whiskey Zulu 5 Mike.
Hey, Scott,
Yeah.
if you're really interested, I did a Google search on a DE9 and a DV9, and it's really a DE9. It's just
Really?
that people started calling them a DV9.
Really?
Yeah, it has to do with the size of the back shell. A DV25 and a DV9 are not the same size back shell. A
I'm
DE,
looking. I see that. Wow. Did not know that. Huh.
I didn't either.
Cool.
For the last 20 years, I've been calling it DV9.
Yeah, as long as I can remember. Right. So can you hear what we're listening to here?
Yeah, I heard that. Yeah, it's a contest.
Thank you, Charlie Radio to Delta X-ray. Norway 8 X-ray, Golf Sierra. Delta X-ray. November Yankee.
Yeah, I have an SDR play, and I listen to the contest now and then to see who's out there.
But do you get the pace? You
That's
get
really fast.
you get the pace and the rhythm.
Victor Echo 3, Victor Victor Norway. Victor Echo 3, Victor Norway.
Contest.
Victor Echo 3. Japan X-ray. Whiskey 3, Japan X-ray, 5931. Thank you, 595. Thank you. Kilo Alpha 3, Foxtrot.
Listen, he doesn't give his own call sign even.
Oh,
Once
he
every
doesn't?
10 minutes. Once every 10 minutes.
3, Foxtrot, Zulu, November.
He's got such a lineup.
Kilo
Listen.
Alpha 3, Fox Zanzibar, November, 5931. QSL 5905. Thank you. Kilo X-ray 2, Tango. Kilo X-ray 2, Tango, 5931. 5905. Thank you. Kilo 7, Tango, Quebec, 5931. Thank you. Alpha Foxtrot 5, Whiskey Alpha. Whiskey Alpha 9, ending radio, 5931. Okay, Whiskey Alpha 9, Mike Sugar Radio. And that's a Zone 3 QSL. Okay, I gotta fix that. Thank you. Whiskey Hotel 7 Tango. Whiskey 7 Papa Lima 5931. Thank you.
Victor Alpha 3, Hotel Delta Lima.
November 8 Japan Oscar Echo, Hi Joe 5931. 03, thanks. Georgette.
Victor Alpha 3, Hotel Delta Lima.
Tango, last letter Tango.
So Stan.
November X-ray 4 Hotel 5931.
Hello, Stan.
Yeah, I'm here.
Was that November
So
Echo
try
4
to
Hotel
picture,
5931?
this is 48 hours.
Thank you. Whiskey Hotel 7 Tango. Alpha Foxtrot.
Yeah, I just brought up my SDR on 21. It's pretty busy.
This is, but the contest is 48 hours long.
3
And
Charlie Mike India, Roger.
He's running an average of about 10 a minute.
Yeah, I see that.
And it doesn't really fade. It doesn't wane. I mean, let's say he sleeps a little bit, right? So he works 40 hours, right? It's 2,400 minutes times, let's say, an average of 6 per minute. You can make 15,000 contacts. He's in Hawaii over a 2-day period.
Yeah. I wonder if he has somebody there taking notes.
Nope. There's no point. That would just slow things down. If you ever do it, if you ever try it, you'll find that it's easier to just be sitting there at the keyboard.
Well, I know that, but don't you want to keep track of who you've made contact with?
Yeah, you do it. You use logging software.
Oh, okay.
Here, like I'll bring up my log from last night. My log is about 3 minutes worth of his stuff. Here, I'll bring up my log from last night.
All right.
Here we go. Here's my log from last night. This is all running QRP. So this is 5 watts. Let me shrink that down. It seems to think that I want to see that, but I don't. There we go. It still thinks I want to see it. No, I don't want to see it. There, I'll scoot it over there. There we go. Now we can see my log. All right. So this is my log starting at 23:48, which is right before 5 p.m., ending at 04:49. Oh no, ending really at 02:30. So this is like 3 hours of operation.
That's quite a few with
5
Morse
watts.
code.
No, it's 5 watts voice.
Oh, 5 watts voice.
Yeah.
Oh, well, that's pretty damn good.
Yeah, and notice a lot of JAs. 15 meters was open to Japan. There's L21F, that's Argentina. SJ2W, there's Sweden. The BG4, about 2/3 of the way down, that's China. Anything that starts with a J there is Japan.
I knew that.
BD7IS, that's also China. BG5TOX. VJ4K, that's Australia. And then as it was getting time to go to bed. The last one I worked was PJ2T, that's Curacao. And that was on 40 meters.
What was that one? P, what was the P?
PJ2T down at the bottom, that's Curacao.
Where is that?
Right off the coast of Venezuela. So
Okay, South
Dutch,
America then, huh?
Dutch island, yeah. Again, that's all 5 watts, just 5 watts and no gain. It's just dipoles.
That's pretty darn good.
Yeah, well, you don't know what you can do until you try it. I always like to, I did not have very high hopes for this. And I was pleasantly surprised. What really clued me into the fact that it was actually going to be pretty good was the fact that I was hearing this. Right, I was working the Japan on 15 meters, and 15 meters has basically been dead for years now, because we've been going through the bottom of the sunspot cycle. And like here, I'm still working Japan on 15 at 6 o'clock. This one right here, that's 6 p.m. I'm still working JAs at 6 o'clock. The sun's almost down.
Yeah. Well, I'm up on 15 meters right now, and I see a lot of activity out there. And there's, yeah.
So is this FT8?
No, this is voice.
Yeah, voice.
This is my log from last night. This is after Nate's ultimate frisbee game. This is what I came home and worked on. This is all 5 watts. 5 watts voice.
Wow.
So
You never sleep, do you?
Yeah, I do. Of course I do. Here. So what I wanted to do was let's look at 10 meters right now. Apparently 10 is in good shape too. Open to South America.
590505. Thank you for 0559.
So there's activity on 10. 20's probably wall to wall. Dan, you see 20 right now?
Yeah, I'm on 20.
Yeah, but look at my picture on the screen. That's the 20-meter waterfall.
Victor Echo 2 Yankee Juliet 5931.
Okay, so this is the guy in Hawaii. I wanted everybody
I'm not
to
either.
hear
I'm on
this.
15.
Kilo Charlie 2 Mike Bravo Victor 5931. Thank you. Juliet Lima Delta 5931.
Whiskey Delta 8, Juliet Lima Delta 5904.
I need your call again. Japan Lima Delta, your call.
Whiskey Delta 8, Whiskey Delta 8.
Whiskey Delta 8, Japan Lima Delta, roger. Thank you. Whiskey Hotel 7 Tango.
Why are they using Japan instead of Juliet?
I do it sometimes too.
Kilo Victor 5 Whiskey
Sometimes it
Sugar
just helps to
5931.
differentiate it. I've got a couple letters that I'll use as alternates. So, because I've got a Juliet in my call sign, so I'll sometimes use Japan, especially if I'm talking to Japan. All right, we're back. It's 12:45. Let's wrap this cool thing up.
Just got home, Scott.
Yep. Oh, that's good. You're here.
Yeah, you can see now. Different background. Yeah.
All right, we are on page number 87. General class operator frequency privileges. Notice they are called privileges, which is a nice way to think about it. So this is what you will have earned by getting your upgrade. So kind of like getting a driver's license. and then getting a CDL on top of it. So, all right. So what we have is you have the question is on what bands do you have access as a general class operator? Well, you look at all the HF bands and you have access to all the HF bands, but not all of the HF bands. So it is important to know that you have full access to the 12 meter band. Well, looking at this, the 30 meter band, the 10 meter band up here, you have full access across the board because we are as a general, you are the blue stripe and the red. So notice also over here where it says G for general. So 10, 12, you have a full access to 17, which is a great band. 30, which is great. Full access to 60 and full access to 160. Heaven help you if you get addicted to 160. Which of the following frequencies is within the general class portion of the 80 meter band? Okay, what is the general class portion of 80? In the phone portion of the band, it's 3.8 to 4.0 because we're looking at the blue stripe. And on the CW and digital portion, it is 3.525 to 3.6. And that's just stuff that you have to memorize. And the more you operate, the more you'll know. When general class licensees are not permitted to use the entire portion of a band, what part of the band is available in most often? And if you take a look, let's say 15 meters.
The upper frequency end.
That would be the upper end. The lower end is extra. Then, believe it or not, this orange stripe, that's advanced. That's the intermediate license between general and extra, which hasn't been given out in, I don't know, 25 years. But there are still advanced class licensees out there. The difference was that in order to get an advanced license, you needed to pass 13 words a minute and the advanced theory. To get the extra, you had to pass 20 words a minute and then pass extra theory exam. So that's why the differentiation is still there. What frequency is within the general class portion of the 80 meter or 75 meter phone? 75 meter phone band. So let's take a look at that band. The general class phone band goes from 3.8 to 4.0. So anything in there, and the answer would be 3,900 kilohertz or 3.9 megahertz. Okay, what are the limits on the 40 meter band? The 40 meter phone band. So we see on the 40 meter phone band, 7125 to 7300. Notice that general band starts at 7175. So you have access from 7175 to 7300. So 7250 is the answer that falls in there. Okay, 20 meter phone band. 20 meter phone band, 14225 to 1435. So anything that falls in there, you have access to. 15 meter phone band. Ooh, this actually changed. This is actually significant. This used to be 21,300 to 21,450. So now it's 21,275 to 21,450. Now you learn something new every day. On 10 meters, let's look at 10 meters. Which of the following frequencies is available to a control operator holding an general class license on 10 meters? What's the answer, everyone?
2.8.
All of them.
Anything.
All of them.
All of them. Any frequency on 10 meters you have access to. Where do you find repeaters on 10 meters? Believe it or not, there are FM repeaters up here.
29.5.
29.5 to 29.7. Those are 10 meter FM repeaters. And why don't we have FM repeaters down here on these other bands?
Bandwidth is too wide.
Bandwidth, that's right. FM takes a lot of space. And the lower you go, there's just not that much room on those bands. On what band are you not allowed to operate any voice whatsoever?
30 meter.
30 meters.
30 meters. 30 meters is CW and data. It's a wonderful band. It has it has properties very similar to the 40-meter band and to the 20-meter band, and it's that nice little in-between space. I worked Lesotho and South Africa on 30 meters last night. Who can operate a 10-meter repeater?
A general class operator.
General class or higher. So what happens if you have a 10-meter repeater that is connected to a 2-meter repeater? And somebody who has a technician class license is using the 2-meter repeater and it's being retransmitted on the 10-meter repeater. Is that okay?
Only if the owner of the 10-meter repeater has a general class or above license.
That's right.
What
So
was the
basically,
question?
yes.
What was the question?
The question is, let's say that somebody is operating on a 2-meter repeater with a technician class license, which is fine. Do technicians have any ability to operate on 10-meter repeaters? The answer is no. You have to have up here to be up in this part of the band. You need to have a general or higher. However, what if you have a repeater system that is linked from 2 meters to 10 meters? A general class operator runs that repeater system, and that technician's voice and call sign pop out on the 10-meter band. That is actually okay. And if they're linked back and forth, it's actually okay for the person on the 10-meter band who has a general to talk with the technician who's on the 2-meter band, because the technician is transmitting where they are allowed to talk. On which of the following bands is image prohibited? Image is like slow scan television. And if we look over here,
30
you will
meters.
see right here, CW, RIDI, and data. It's CW, RIDI, and data are the only things permitted on the 30-meter band. Notice this also says avoid interference to fixed services outside of the US. This is actually a shared band. We are not exclusive users of this band. So you will sometimes hear something like radio location or satellite or weather radars or things like that on that band. And that's why it says avoid interference, because we're not the only users. Another one down here where we're not the only users is the 60-meter band. Notice this is very important. Maximum 100 watts ERP. So this is a good discussion. What does ERP mean?
Effective radiated power.
Effective radiated power. That's right. And so that takes into account your antenna gain. You are allowed 100 watts ERP. So if you have a gain antenna, that has to be calculated into your ERP. And notice it also says channelized, which is really weird because all these other bands are not channelized in any way, shape, or form by law. 60 meters is, because it was created, essentially carved out of another band. The military has access to these, and in Alaska they actually had access to them for emergencies, right? Our Alaska person. All right, where'd he go? Did we lose him? Hello, hello. Oh, come in, Alaska. John, are you there?
No, but I'll interject. When I was in the Navy back in the 70s, this 60 meters is what we use for basic RIDI communications.
Yep. Well, we're allowed to use it, but now notice we have data channel center and USB tuning frequency. This basically means that our signal has to be centered on the band, which is really weird. And there are 5 channels to use, and that's it. It makes it kind of a weird place. So I have not spent much time on 60 meters. I've heard it's interesting, but I haven't spent a lot of time there. On the 30 and 10 and 60 meter bands, we are a secondary user. This means that we may come across somebody who is a primary user. That also means we are not allowed to cause interference to primary users. We are there and they are there first. So on other ham bands, we are primary. On the 60 and 30 meter bands, we're secondary. So we have to move if we're interfering. If a primary service interferes with your contact on the 30 or 60 meter bands, they're primary, we're secondary. You need to actually move to a clear frequency. That's your duty to do so.
Hey, Scott, where do the FRS and GMRS frequencies come in?
They're way up here. FRS and GMRS, they are above 450.
Okay.
They're way up there, which is why their antennas are so tiny.
Hmm.
Yeah, FRS and GMRS are at 462 and
462 to
467.
467.
467. Okay. The frequency allocations of which ITU region apply to radio emitters in North and South America. Okay, so it's a good idea to show the ITU map. So I'm going to have to pull up the ITU region map. Here we go, ITU regions. There we go. There are the ITU regions. Notice that we are in the blue, that is region 2. And Europe, I believe, is region 3, and region 1 is the Pacific. Here we go. So region 1 is much of Northern Asia, so basically Russia, and down into Africa and Europe. Region 3 is the Pacific, and region 2 is the Americas. They all have different rules. There's a lot of overlap, but they have different rules. So one interesting thing you'll find is that if you live in Hawaii or you visit Hawaii, you are actually in a different region, if you potentially. If you go to Guam, you are definitely in a different region, and your United States license covers different things than you would be expecting it to cover. Which of the following may apply in areas of FCC jurisdiction outside of region 2? Frequency allocations may occur. They may be different. Sorry. Okay, let's see. What's the maximum height above ground you can put an antenna structure without telling the FAA and registering with the FCC?
200 feet.
200 feet. So a friend of mine back in Maryland, W3LPL, is a big time contester. And I'm going to bring up W3LPL's website or his QRZ page. And there is his nice little ham farm. There's his antenna farm. Everybody see those antennas? He had several towers that were at 199 feet, 11 inches. Because that's as high as you could go without telling the FCC.
That's a lot of towers.
That's a lot of towers. He has 12 operating stations in his basement.
So he's got lots of money.
Lots of money. Yes, he does. Under what conditions are state and local governments permitted to regulate amateur radio antenna structures? Well, basically by PRB1, which is one of the rules that the FCC managed to put through, we basically must be reasonably accommodated. So regulations must constitute the minimum practical to accommodate a legitimate purpose. Essentially, there's that term reasonably accommodated. Now, that actually covers, notice, state and local governments. Unfortunately, it does not cover homeowners associations. So your homeowners association can tell you to get lost. They don't really have to let you put up an antenna. You still have to, you're still allowed to like put up a satellite dish. I think that's by law, but they don't have to make accommodations per se for you to put up an antenna, an antenna in the trees. Now, more than likely, a lot of them are not going to complain about it, but if you try to put up a tower, if you signed into a homeowners association, you're probably not going to be allowed to put up a tower.
One quick question, Scott.
Uh-huh.
The 200 meter foot limit, is that within a certain zone of an airport or?
Nope. That's
Nope.
period. At near airports, it might be lower.
That's what I'm asking.
Yeah. You're not near anything. Why, are you going to put up something big?
I was in real close to the airport before I moved here, and I wasn't sure how tall a tower that would be allowed. So that's-
Yeah.
And it's 200 feet, not 200 meters.
Right, it's 200 feet. Yeah, nobody can afford to put up a 200-meter tower by themselves. Which of the following is a purpose of a beacon station? A beacon is something that goes, I'm here, I'm here, I'm here, I'm here. That's one-way communications. It's specifically one-way transmissions designed for observation and propagation and reception. The power limit for a beacon is 100 watts PEP. And what does PEP stand for, everyone? See if you remember.
Peak envelope power.
Peak envelope power. That means the maximum power that can be spit out by the station is 100 watts, period. Beacon stations, there must be no more than one beacon signal transmitting in the same band from the same station location. So that means you could have a 20-meter beacon, you could have a 15-meter beacon, you could have a 10-meter beacon, 6-meter beacon, 2-meter beacon, but you can only have one at any given location on any given band. On what HF frequencies are automatically controlled beacons permitted? Well, let's look at our 10-meter band. From 28.2 to 28.3, right in this area, you're allowed the beacon band. And just for fun, I'm going to take a look. I don't have it open. Darn it. I thought I had it open. Okay. Why should an amateur operator normally avoid transmitting on 14.1, 18.110, which is right here, 21.15, which is somewhere down in here, 24.93, and 28.2 up here. Those are where beacon stations live. So if somebody is listening for beacons to observe propagation, and you transmit on those frequencies, what you're doing is obliterating their ability potentially to hear the beacon stations and figure out what the propagation's like. So you would be interfering with the beacons. Which of the following transmissions is prohibited? Occasional retransmission of weather and propagation forecast information from US government stations. So
What?
that could be talking about the weather over the Pacific Ocean, for instance. That could be of use from, NOAA to everybody. So you could actually retransmit that over the air. What one-way transmissions are permitted? That would be international Morse code transmissions, such as W1AW code practice. There's nobody listening on the other end that's expected to reply. Everyone's just practicing. When is it okay to communicate with amateur stations in countries outside areas administered by the FCC? Basically, if those other countries have said, we don't have any problem with it, then it's okay. What are the restrictions on the use of abbreviations or procedural signals? So that basically means if something is well known, for instance, Q signals, QSL, but let's say you invent your own Q signal and only you and a friend know it. Is that okay?
Nope.
That is not. Now, you could publish it if you make a reasonable attempt to publish it and let everybody know that we're inventing a new Q signal and we're going to use it. QLOL, right? Okay, well, just so everybody knows, we're publishing the fact that QLOL means I'm rolling on the floor laughing. Then that might be okay. But it's something that has to be made publicly available. What must be done before using a new digital protocol on the air? Same thing. You have to tell everybody what the digital protocol is and how to decode it. So you have to publicly document it. When choosing a transmitting frequency, what do? Well, you ensure that you're allowed to be there. You check the license, you check the privileges. So let's say that we're looking at I feel like transmitting and I look at 14.160. Like, oh, look, it's frequency's free. But then I look here and say, oh, I don't have an extra class license. I can't be there. So it's not within your privileges. So you can't be there. The second, once you do find a frequency, oh, okay, I found an open frequency at 14.275. Okay, Well, that's a general class license. Then you listen and listen and listen and make sure, okay, well, what's the mode that's operated there? Well, according to this chart, it's general voice. All right, well, I'm good to operate upper sideband there. And then you will listen on the frequency to make sure that it's free. And finally, you would do what?
Ask
Class
if
EQ.
anyone's on the frequency.
You'd ask if the frequency is free. That's right. Okay. What determines good engineering and amateur practice?
FCC.
The FCC determines what is good engineering and amateur practice. All right. And okay, we're now moving on to page 93. And this is actually really important because this determines how much spectrum you can use and how much power you can use. So we're going to pull this back up. We're going to go back to our frequency spectrum chart. Okay. By and large, we are allowed to operate with a maximum of how much power? How many watts?
1500.
1500 watts with some exceptions. Okay, so here we go with the exceptions. The limit for transmitter power on the 28 megahertz band, 28 megahertz is also known as what?
10 meters.
10 meters. The limit there would be 1500 watts, PEP, or peak envelope power. On the 160 meter band, which is also 1.8 megahertz, 1500 watts. On the 12 meter band up here, which is 24.89 to 24.99. How come we don't have 25.0?
That's
Anybody?
time.
That's the time. That's one of the time channels. That's right. WWV is up there. That's why we don't go up that high. On that on that band of frequencies, however, on 12 meters, 1500 watts. Okay, this one is actually really important. We look at 30 meters. Notice this right here, maximum power, 200 watts, largely because that is a shared band. We don't want to interfere with anyone, so that's a lower power band, 200 watts. Which of the following is required by the FCC? Okay, so notice this little ERP. This says ERP. What does ERP stand for again?
Effective radiated power.
Effective radiated power. That includes the gain of your antenna. So you're allowed 100 watts, but it is 100 watts effective radiated power. So if you have an antenna with 10 decibels of gain, how much power could you actually run?
10 watts, right?
10 watts, that's right, because 10 dB is 10 times. So you could only run 10 watts, and you would have to keep a record of the antenna that you were using. Okay, what measurement is specified by FCC rules regulating maximum power output? That word again is PEP. This is going to come up over and over. PEP is peak envelope power. That is the biggest, largest, tallest amount of power that can come out. It's if you look at the envelope of your signal, it is the most that it goes to, the highest level of power that it goes to at any point in time. Which of the following limitations apply to transmitter power on every amateur band? This is something that is actually written into the rules. Okay, so let's look at this band on 12 meters. How much power are you allowed to run? How many watts?
1500.
1500. What do the FCC rules state? How much power should you run?
The least amount needed.
The least amount necessary to carry out the desired communications. So whatever those communications are, you decide what that is, you have to use the least amount of power. And why would we want to do that?
Avoid interference with other stations.
Exactly. It basically, because bandwidth is a resource, so that potentially frees up that resource for other people. Okay, what's the maximum bandwidth permitted by FCC rules on the 60 meter band if you're using single sideband?
2.3 kilohertz.
2.8. So what do we normally think of as the bandwidth of a single sideband signal?
3 kilohertz.
3 kilohertz. On the 60 meter band, the maximum that we can have is 2.8 kilohertz. So what does that mean, practically speaking? That's a good question. I think by and large, most equipment that is produced today will actually comply with that, but technically the maximum bandwidth we're allowed to run is 2.8 kilohertz. All right, and this is actually really important. This whole section on bandwidths and data rates. Okay, what is the maximum symbol rate permitted for data emissions on the 20-meter band? And that would be 300
300.
baud. Okay, does anyone remember a 300 baud modem?
Nope, not old enough. Sorry.
Yep, I do.
I do. And what was special about that 300 baud modem?
Don't remember.
Did you have one that actually you plugged a handset into a receiver? Did you ever
I think I may have had one once.
Yeah, where it basically it was audio coupled. You would actually take the handset and go clip and you'd plug it in and it would audio couple the audio, it would audio couple the speaker and the microphone. That was 300 baud. 300 baud is really, really slow. So the question now becomes, why are we so limited in speed?
Bandwidth.
Bandwidth, because data takes up space.
Bandwidth. Yes.
That's
space.
right. Data takes up space. So on the 20-meter band, the whole band is only 350 kilohertz wide. So the limit for sending data is 300 baud, which compared to PSK31 is still pretty good. You know, it's still pretty, it's not fast by any stretch of the imagination, but it's still permissible. All right. On 10 meters, because it's a much larger band, we have 1.7 megahertz of space. The data rate there goes up to the blazing fast 1200 baud.
Mhm.
Anywhere below longer wavelengths, it's 300 baud. So 12 meters all the way down, it's 300 baud. So when we go up in frequency, we have more and more space. On the 2-meter band, we're allowed 19,600 baud, which is getting up to reasonable speeds. On
What about 6 meters?
6 meters, I think so. I don't remember for sure. On the 220 band or the 1.25 meters, we've got 56 kilobaud. On 70 centimeters, we've also got 56 kilobaud. So if we want to do any high speed stuff, relatively high speed stuff, the 420 to 450 band right here is typically where we would start. Now, if you go even faster, you get up to Wi-Fi type of speeds. You get up to, let's say, the 2.3 gigahertz band or 2.4 gig band or the 5.8 gig band. Matt, how fast can you go?
That I don't know.
Okay. Well, but we're into the mesh stuff at that point.
Pretty much, yes.
You know, modified ubiquity routers and things like that. So the bandwidths are quite high because there's a lot more room. Okay, we are now on to volunteer examiners and such. Okay. Who accredits volunteer examiners?
A volunteer exam coordinator.
Volunteer examiner coordinator. So not the FCC. The FCC has assigned 14 different volunteer examiner coordinators to coordinate all the volunteer examiners. So the FCC has the group of volunteer examiner coordinators. They pick their examiners and they accredit their examiners. As a general class operator, can you be a VE?
Yes.
You can. Okay. You can be a VE. You have to be a general or above and hold a US radio license. Okay. So how old do you have to be?
18.
18. And what exams can you give as a general class?
Technician.
Yep. You can give technician class exams.
Oh,
All right.
sorry.
So an extra can give general class exams. So who gives extra exams?
Other extras.
Other extras. Yeah. It kind of falls apart at that point. All right. So as a general VE, you can get it. You can give technician exams. So, and you also have to be accredited by the FCC. How many examiners does it take to? You guys have all taken exams. How many examiners does it take to proctor your exam?
3.
It takes 3. That's right. Okay, and not that you've ever gotten one, but let's say you passed an exam and it was not immediately applicable for a license. You get a certificate of successful completion of examination. How long do you have before that's no longer good? Well, it's not 1 year.
It's
They've actually codified
365 days.
365 days. So if it's a leap year, you lose 1 day. That's right. That's good for 365 days. This used to be very applicable when it came time to code tests and written exams. Like you could pass a code test and not be ready to take the written exam yet. That would be your proof that you'd passed a certain code exam. On which of the following band segments may you operate if you are a technician class operator and you hold a general class CSCE?
On any general or technician segment.
That's right. So this is really important because depending on who you examine with, do you have a license? Yes or no? Without a license in the database, you cannot operate, correct?
Correct.
But you are in the database. You're in the database, but you're listed as a technician class operator. So this occasionally happens. In fact, it just happened on in our Now What Net a couple of weeks ago. Sue, I believe you got the rare opportunity of saying /KT, did you not?
I did, and nobody asked me about it, which I was kind of surprised at.
I knew what you did. I knew what happened. I thought it was really cool because the
Yeah.
only way to get a /KT would be to upgrade from the novice to a technician, which is really rare now.
Really rare, and it also happened because I took the test on Sunday, and Monday was a holiday, and
That's
I was
right.
on the net on Monday, so
Right.
the FCC didn't have my license upgraded yet.
That was a extreme rarity. It's more likely that you'll hear somebody say /AG, which is a general class.
That's actually what they said to me on the examiners said to me when I took the test. You'll have to put a /AG after it, but then I read my certificate of successful
Oh.
completion, and it actually tells you what modifier to add.
Okay,
So.
I have a question for you then, because we're
Mhm.
getting close to the end. This is really kind of cool. Why is it KT and not KG? Or why is it KT and not AT?
I don't know. I mean, T is for technician, I think.
Yeah,
G
it
would be
is.
for general. So
And AE would be extra. How come AG and AE are valid and AT is not?
maybe because the novice classification is grandfathered and not.
Well, for an
Active
advanced,
signal?
it used to be /AA.
Oh, okay.
So why is AT not permitted, but all those others are? And
I
this
don't
comes
know.
back to what we have as prefixes in the United States. We have AA through AL as American call signs.
Mhm.
AT is Spain.
Mm.
So they had to pick a different one
Ah,
for
okay.
technicians because AT didn't apply.
Okay.
Yep. So you got to do something really, really unusual.
Yay me.
Yeah. All right. So if you have a certificate of successful completion of examination, you get to sign /something if your license has not been upgraded yet. For a general, you would say /AG, amateur golf. You'd say alpha golf or AG. Who can receive partial credit for elements represented by an expired license? Basically, if you ever held an FCC General, Advanced, or Extra that wasn't revoked, you can actually get credit for that if you show if you can provide the examiners with a copy of the license or show where in the call book your call sign was listed. What's required to obtain a new general class license after a previously held license has expired and the 2 grace year period is gone? If you pass the element 2 exam, if you pass the technician exam, you get all your old privileges back, so long as you can prove that you actually held it, which is a fairly new thing. It's actually kind of cool. All right, control categories, repeater regulations, harmful interference, and so on and so forth. Okay, what type of messages for a third party in another country can be transmitted by an amateur station? The same things that we are allowed to do here. Remarks of a personal character, which is, oh, my back hurts. I have a doctor's appointment next Tuesday. Or I hope the kids are doing well. Or what's the weather like? It's sunny here. Or emergency or disaster relief information. So you can send lists of people who would like to, who are being reported as being okay. Which of the following would disqualify a third party from participating in stating a message? If a third party is an amateur licensee that got their license revoked and not reinstated, you are not allowed to have them use yours. Okay, which of the following conditions require a licensed amateur radio operator to take specific steps to avoid harmful interference when operating within a mile of an FCC monitoring station? That's a new one. When using a band where the amateur service is secondary, as we already saw, there are a couple of bands that are like that. One that wasn't really mentioned because there's 30 meters and 60 meters, right? The other one is 70 centimeters. We're actually secondary there. We have a lot of space, but we're actually secondary. And when when a station is transmitting spread spectrum emissions, that means we are actually allowed to operate spread spectrum, but that means that we actually take up a fair amount of bandwidth. So if we're causing interference, we need to back off. On what bands can automatically controlled stations transmitting RTTY or data communicate with each other using automatic stations? Well, the first thing is that your frequencies have to be on the 6 meter band or up. So 6 meter band or shorter wavelengths, and in a few sections on the HF bands. So basically you can run automated stations anywhere on 6 meters and up, and on a few HF bands here and there. What is required to conduct communications with a digital station operating under automatic control outside of the automatic band segments? Well, if it's outside of the automated band segments, the initiating station must be under local or remote control. Because as if everybody remembers, there are 3 kinds of control. There's local, which is my hand on the push to talk button or on the keyboard. There's remote, which is I'm controlling a station over the internet or over some other link. And there's automatic. Automatic is a repeater. It could also be like a link station between stations, like an auxiliary station. That would be automatic control, automatically forwarding information. So if I'm outside of automatic control bands, I would actually have to be a manual initiation of a connection. And we're just about at the end. In what part of the 13 centimeter band? Okay, 13 centimeter band doesn't even show up on this chart. So, but looking at this, Matt, what is the 13 centimeter band?
Oh my.
You know this one.
I really don't.
2.4 gigs.
Okay.
13 centimeters is a 2.4 gigs band. That is 2400 megahertz. And what do we share that band with?
Bluetooth.
Bluetooth, Wi-Fi, et cetera, et cetera.
Bluetooth, Wi-Fi, whatever.
Channels 1 through 11. So we share those frequencies with all those Wi-Fi signals. Who can we communicate with in the Wi-Fi band?
No one.
We can communicate with other ham stations. So Wi-Fi stations are not licensed, and we are. So therefore, we are allowed to talk to other ham stations and not people in the Wi-Fi arena. The maximum PEP output allowed for spread spectrum. Spread spectrum, we're allowed 10 watts of power output, PEP. So I guess one question that I would ask is Wi-Fi considered spread spectrum?
Can be.
It can be. Yeah. So I think, Matt, are we on the ubiquity stuff? Are we limited to 10 watts because of that?
I don't know.
Oh, that's homework for everybody. I expect an answer from somebody because I don't know the answer to that one. Okay, and finally, under what circumstances are messages sent by digital modes exempt from Part 97 third-party rules that apply to other modes of communication?
Under no circumstances.
Under no circumstances. In other words,
Nope.
basically, if you're sending messages and somebody asks you to send a message and it is, let's say, oh, we have we're having a big car lot sale tomorrow, right? That would be a third-party message from somebody. You're not allowed to send that because it's a business message. So the same exact rules that apply to the amateur service apply to third-party messages as well. And that's the whole thing. Give yourselves a big round of applause as you did the entire thing. All right, so now, that being said, there's a 35 question exam, which I don't have access to, but you guys do. And I have actually recently done an exam just to make sure I could still do it. In fact, I went through the entire question pool to make sure that I actually knew how to do the question pool. So, I mean, because otherwise, what kind of a teacher would I be, right? So, I am curious if anybody has any questions or anything like that before I turn you all loose to go and practice and get ready to someday schedule an exam and take a test.
Yeah, Scott?
Go ahead, Sean.
Oh, thank you. Back in 2018, when I took my technician exam, they did not have a Morse code requirement to do for those tests. Has that changed any?
Nope.
No. Okay, so there's no Morse code for the general exam.
Morse code is a voluntary thingy.
Okay, thank you.
I teach it because I really like it.
Okay.
And I will continue teaching it because I really like it. And actually what I found is that people, now that they don't have to learn it, are really eager to learn it because it has value. They're seeing that it has value on its own. So, all right, who else got their hand up?
I have a question about telescoping antennas, right?
Yep.
So if it telescopes and I push in, say, one segment, have I shortened the length electrically of my antenna?
You've essentially bypassed some of it.
And so if I do that, does that end up risking damage to, say, my radio transmitting on something with a bad SWR?
All right. Well, part of it is we can answer that by asking, what is the length of the antenna as it stands? How long is it extended?
Well, so it's about 15.6 inches, I think.
Okay. Does it have a loading coil at the base?
That might be a loading coil.
It's a loading coil. Yeah. Okay. So the question then becomes, if that is, when extended, if that is a tuned antenna that is designed to be resonant on that particular frequency, what do you think would happen if you shortened it? What would the resonant frequency do?
The resonant frequency would go up.
Resonant frequency would go up, and therefore it would not present a proper match at a lower frequency, which at the very least would make it inefficient.
Right.
Right. And okay, so now the question is, let's say that you have a transmitter that's capable of transmitting 5 watts. Okay, so it has to generate enough voltage internally to generate 5 watts of transmitted power. So let us say that you transmitted 1 watt. You turned the power down to low and it was transmitting 1 watt. Then you disconnected the antenna completely. And you transmitted at 1 watt. Where would the RF power go?
It'd just go back into the...
It would go back into the transmitter. Okay, so now you have to dissipate all of that heat using the transistor. I mean, it's got to go somewhere, right? So, but it's designed to run 5 watts at a certain efficiency. So more than likely, if you do that, you will be okay. What happens if you transmitted 5 watts with no antenna? And the amplifier didn't have any kind of protection circuitry?
Well, then it would probably burn out.
It would probably burn out, because let's say that your efficiency is 50%. So in order to generate 5 watts of RF, you have to dump 10 watts in, which means you're burning up 5 watts in heat,
Gotcha.
right? You might be okay. But let's say that your transmitter, because it operates class C, because it's an FM amplifier, is 75% efficient. In which case, then to transmit that, to send out that 5 watts, you actually have to make about 6.5, which means that it's only really designed for about 1.5 watts of heat dissipation. Because to make 5 watts out, it has to get rid of 1.5 somewhere. But now you disconnect the antenna, and all of that energy, 6.5 watts, has to go somewhere. So unless it can say, oh crap, there's something really bad happening, and knock down the power level in a hurry, you're going to be dissipating all that energy into at that heat sink in the components, and they might let the smoke out at that point. So the question then becomes, what kind of a load does your shortened antenna present? And the thing is, I don't know the answer to that.
Sure.
It's not going to be properly matched, but it's not a short circuit and it's not an open circuit, which means that at low power, it's going to be horribly inefficient, but that might be fine. And at low power, there's probably not enough energy coming back into it to destroy anything. So you'll probably never notice.
Okay. Thank you.
Go ahead, Matt.
No mention or discussion of lead acid batteries so far.
I thought very briefly we talked about them. What about them?
Are they safe to charge indoors in your ham shack?
Okay. Is it a sealed lead acid or a wet cell?
It is a flooded wet cell.
So like a car battery, or when you say that, is it a
Deep cycle.
deep cycle? So is it but is it a VRLA or a gelled cell or a
No.
absorbed glass mat?
Nope.
So, the risk there, of course, is that
Hydrogen.
yeah, you basically you develop hydrogen if you overcharge it or undercharge or over discharge it. So, I've got a sealed lead acid. I've got a 75 amp hour sealed lead acid under my desk out
Okay.
in the shack, and I have it's a gel cell or absorbed glass mat or whatever it is. And I don't particularly worry about it, because I think it's a lot safer than like a wet cell car battery. And I have it on a charge controller that limits the charge rate and limits the voltage. So, that being said, I don't think I'd want a car battery inside my house if I could avoid it, because
Okay.
I think that's more likely to generate hydrogen and spill, and because you actually, instead of having a gel, you actually have liquid sulfuric acid in a wet cell.
Yeah.
So
Yeah, invest
if
in
something
a
were,
good
yeah,
lithium iron phosphate or something.
yeah. Well, I have a parent of a friend of mine who had a dead car battery, and they were doing a jump start, and they say you go hot to hot and then ground to other ground on the other car. They didn't do it in that order, and they generated a spark right over the positive terminal.
Yeah.
And it blew up their sulfuric acid battery.
Okay.
Yeah, the hydrogen ignited and it blew up the battery, and there was a shower of sulfuric acid. So
Not fun.
not fun. Any other questions?
I got a quick question.
Okay.
Down the street, there's this antenna. I was just kind of wondering what you could tell me about.
Well, let's see. That is, let me make it nice and big. I want to pin that, and oh wow, that's pretty cool. Okay, where exactly are you? What area?
This particular antenna is at about 20, let me think here, 22nd and Madison.
Wow, cool. Okay, so, okay, you see how it's got the big section in the center? The big element? So
Okay.
that looks to me like it's, let's see, 1, 2, 3, at least 4 elements on the intermediate, then a smaller one. So that could be like I mean, depending on how big it actually is, I can't tell how big it physically is.
Oh, it's probably, I would guess it's probably at least 12, 6 feet off each from center. It's at least
Okay.
that.
Actually, that's not that big.
Maybe
so
it's
if that-
bigger than that. I can't recall for sure.
Yeah, if that's the case, that could be like the one in the center is probably like a 20-meter rotatable dipole. Essentially, what that looks like to me is 3 antennas on one boom. Because notice they don't look like they have traps. Each antenna just is a piece of aluminum, right?
Yeah.
So more than likely, that's like a 20-meter rotatable dipole in the center, and then like a 15-meter 1, 2. It looks like a 4 elements on 15, and 1, 2. Let me count. 1, 2, 3, 4, maybe 6 elements on 10. And they're spaced so they don't interact with each other. So you get limited gain on 20 meters, but then it looks like 4 elements on 15, which is a pretty good gain, and then 6 elements on 10, which is really good. That would be my guess. But without a frame of reference, it's a little hard to tell.
Right. Well, I'll have to check in with him sometime to find out what it's all about.
Well, who is it?
I don't know.
Yeah, you got to go knock on his door.
Yeah, right.
That's the important part. You got to knock on his door and find out.
Yeah.
Cool. Anybody else?
Thanks, Scott. Appreciate it.
Well, I appreciate you guys spending a couple days with me here. I know it's a lot of material, but you've now unlike the technician class, it's up to you guys. Yeah, I mean the technician class is still up to you guys, but the benefits to upgrading are pretty obvious. So go for it, everybody.
All right. Well, thanks so much.
Thank you, Scott.
Thank you so much.
Thanks a lot, Scott.
Very helpful.
All right.
Thanks a lot, Scott.
And if there's anything else that you're in the middle of studying and saying, I just don't understand this, I personally recommend using the ham radio exam. This is even more so than the hamstudy.org. It's the ham radio exam general app, iPhone, and I guess it's mobile app. The reason I like that one is because it's actually broken up. There's like 10 different sections of the question pool, but then there are subsections within that. That actually allows you to study like groups of like 10 questions from each subsection at a time.
Yeah,
and practice
definitely
them.
helped. I've made a huge difference for me using that app.
Good.
Good.
So, all right.
The app is hamradio.org.
No, well, no, there's hamstudy.org. That's the online thing. Nate, I hope you're dressed. I'm leaving in 10 minutes, Nate. The other one is ham radio exam. I'm going to write it in there. Dash general. And it's by Roy Watson.
There's another really good one. hamradioschool.com.
Is that one free or you got to pay for it?
The book costs, but the exams are free.
All right. The reason I like ham radio exam general is because it's completely FREE. So it's well written and it's free. So
oh, this one's extremely well written.
Yeah.
I got all of this and didn't want anything else.
Well, let me ask, what did you guys think of the book we're using here?
I personally didn't like it.
Okay. Well,
yeah, go ahead.
Go ahead.
I felt that, going through the book, the way that it like gives you just basically question, answer, question, answer, question,
Yep.
answer. It really does focus in on what the test is, but then with the format of the class, I feel like we spent a lot of time just basically reciting the question and answers from the book rather than talking about the principles involved. Now, when we did talk about the principles involved and stuff like that, and the explanations, I felt like those were the more valuable parts of the class, and the
Okay.
parts where we just went, basically reading the book. Well,
Yeah.
we could have more or less read the book on our own, or
Right.
as you go through the practice tests, find what the answers are. And so it's less valuable to sit and listen to the
The
book be
teacher
read.
read. Yeah. Well, I try to avoid that. I hope it wasn't mostly that.
No, it was good. This was definitely worthwhile doing. It wasn't like a waste of time or anything.
Okay.
Then Scott, you're gonna post today's video, right?
Yep. In fact, let me go ahead and stop.